I'd like to welcome and thank everyone for joining us for today's AVS webinar on plasma-assisted atomic layer deposition, basics, equipment, and applications. Your presenter today is Erwin Kessels. He's a professor at the Department of Applied Physics at Eindhoven University of Technology in the Netherlands. So he is here, I believe, late hours his time to present this webinar for you. I'm going to go through a few slides here before we begin and make sure everybody gets logged in. So let me go from here. You were sent presentation slides to download and save in advance with your login email. So hopefully everybody's got that in advance. If you have any questions during the presentation, please find the Q&A feature on your screen. You can type in questions there and Erwin will do his best to answer them as we go along or as we return or take each break. If you're having any technical issues or have any AVS related questions, please type them in the chat feature and I will try to assist you there. We will be taking hourly breaks of approximately 10 minutes, give or take, and hopefully have a final Q&A at the end of today's webinar. We have some upcoming training. I'm going to be brief on some of these so we can make sure Erwin has enough time to do his presentation. But we do have an online short course program coming up in March with several courses taking place. These are full-day courses running from 10 a.m. to 5 p.m. Eastern Time via the Zoom platform. We do have registration open for this schedule here. So if you see anything on this, you can register today or anytime before that. We also have an ICM CTF 2023 short course program. These are in-person courses. There's 8 half-day courses. Again, these are in person at this particular conference taking place in San Diego. Registration is available online. And we have an upcoming e-talk on surface microscopy and microanalysis in an industrial research laboratory. We are setting up registration for this, but this will be available in April. It's a 1-hour free e-talk, so please check it out. And we have several upcoming conferences. The one I mentioned earlier with the short course program is the ICM CTF in San Diego in May. We have ALD, ALE 2023, which Erwin is very much a part of for this event. And so he's got a lot of information on this topic. So this webinar will be filled with information you'll be able to apply and hopefully you'll want to attend this conference. Then we have the MIOMD conference in August. That's in Norman, Oklahoma. The gallium oxide workshop is also taking place in August, and that is in Buffalo, New York. We have NAMBE 2023 in September in Madison, Wisconsin, and we have opened up our abstract submissions for AVS 69, our International Symposium and Exhibition. This will be in Portland, Oregon in November. All these can be found on the AVS website on the events calendar, so please look for that. If you're not already a member of AVS, we encourage you to join. You can meet new people, work, collaborate. You can have access to some of our journals, opportunity to volunteer and develop leadership skills, and it also gives you discounts on various meetings, subscriptions, and more. So check it out. If you have any questions, you can reach Angela Klink. She's our AVS Member Services Administrator. She can outline the information or any questions you have. We have student chapters. We encourage students to participate, and we also have career services for technical library and more. Finally, I'd like to remind you there is an online evaluation form for today's webinar that we'd like you to complete. And now I'd like to bring in Erwin Kessels to present plasma-assisted atomic layer deposition, basics, equipment, and applications. Erwin, thank you for joining us, and I'll let you take over from here.
Okay, thank you, Heather. Thank you for the introduction. Let me just open up the slides. Oh, that's too fast. Start here. And let's start taking the pointer. Well, okay. Let's get started. So first of all, a very warm welcome. I'm very happy that many of you are attending this webinar about plasma-assisted ALD. Just let me point out the disclaimers and the copyright notice here. But I very much would like to get started right now. So I will talk about plasma-assisted ALD today. The same name is plasma another name is plasma enhanced ALD. That's very similar. That's the same thing. So I will use also the terminology. Sometimes I will say plasma assisted ALD. Sometimes I will talk about plasma enhanced ALD. It's just the same thing. And as the title shows, I will talk about the basics, the equipment, and the applications. Just a very short introduction of myself. So I'm a professor at the Eindhoven University of Technology. I'm leading the plasma materials group. I worked, all my professional career, I worked on thin film synthesis, thin film preparation, mostly by plasma-based methods. And since 2002, I started the ALD activities. We do all kinds of ALD, but our emphasis is on plasma-enhanced ALD, and hence also that I'm giving this webinar. And of course, with an ALD, and when you use plasmas, then plasma physics, thin film physics, and surface science all come together. Yes?
I'm just going to ask some people, is there anybody else who's not able to see the screen? I have someone on our chat who is not able to view the screen just now. And if anybody else is not seeing it, please let me know in the chat. All right. I'm not seeing anybody comment in the chat, so I'm going to see, I will type this person and let them know to log back in. Thank you. I'll let you continue.
All right. Well, I also like to highlight two other things, or three actually. So I'm also an associate editor of journal Vacuum Science and Technology A and B. So that's a very important journal actually, where a lot of ALD work is published. Also the organizer of the ALD Academy. And another important aspect here is I'm also take care of the Atomic Limits blog. And actually we refer to this blog several times throughout my presentation, because you can find some very useful information about ALD and plasma-assisted ALD on that blog. So I will have several links to that blog throughout my presentation. So I understood there should be 44 participants right now, so that's maybe also good to know. I'm very happy about this number. Most people coming from the Americas, but also some people from Europe having a late nights work, and some people that are very early from Asia. And as you can also see, most people are coming from industry, and the rest is from academia in institutes. Well, what I really hope is that I will be able to present to you and discuss, present to you what plasma-assisted ALD is, and that you have a very good role also about some fundamental aspects, the role of reactive and energetic species. That's a very important aspect of ALD. I'll of course discuss the equipment and discuss several applications and processes and material systems. And with all of that, I hope that you can really understand the pros and cons of plasma-assisted ALD with respect maybe to thermal ALD, and that you can make a wise decision in the future when you want to use ALD for your application. And as said, as already clear, don't hesitate to ask questions, put them in the Q&A, and I will do my best to answer them after every block, but also at the end of, otherwise at the end of the webinar. So I have divided the presentation in 4 blocks. As you can see here, I will start off quite easily with basics of ALD and processing plasmas. Then I will talk about plasma-assisted ALD equipment. Then we go a little bit more deeper into some fundamental aspects by looking at plasma surface interaction, and then I will close off by discussing some applications and processes. So the first thing that we're going to do is talk about atomic layer deposition, and especially, of course, plasma-assisted ALD, and also some basic aspects of processing plasmas. Maybe some of these things are might already be known to you, but I think it's good to go over these things to bring everybody on the same page. So I will start with this slide. This is the market size of deposition wafer fab equipment. It's data from 2019, so it's a little bit outdated, but I had a projection for up to 23 here. And what you see is that ALD has become a really important technology in semiconductor industry. So ALD is now as important as PVD, for example. And this fits the trends in thin film requirements in the semiconductor industry. We need thinner films, we have taller structures, so we need more conformal films, and also we need to work at lower temperatures. So that explains the interest in ALD, and certainly also the interest in plasma-assisted ALD, as will become clear throughout my presentation. Now, ALD is, before I really go into detail, I will just point out what are the key features of ALD. So ALD is a method to deposit thin films, atomic layer by atomic layer, and it's therefore a truly enabling thin film nanotechnology. And here you see basically the key features of the ALD. So first of all, we have this very precise thickness control because we deposit films atomic layer by atomic layer. The other important thing is that we can have a very good uniformity on large substrates, 300 millimeter wafers or big glass panels, no problem for ALD. Then we have an unparalleled conformality. So if you have 3D structures, you can have very conformal coatings. And that means that you have the same thickness everywhere, also in these 3D structures. And then the last aspect is that you can do all of this at fairly low temperatures, so typically below 400 degrees C, but with some processes even working at room temperature, certainly the plasma-assisted ALD processes. Now, of course, it's used a lot for wafers in the semiconductor industry, but you can also apply it on flexible foils. If you have 3D structures, no problem to, well, generally no problem to coat them conformally, so you can do this on trenches and vias, but also on nanowires and nanoparticles, or you can actually penetrate films in porous substrates. The method is often used also for encapsulation of any device. You can do selective deposition if you have a pre-patterned surface by ALD. You can make nanolaminates where you alternate between different materials, or you can do delta doping. And there are many, many other applications. So you can use ALD for many nanoscale engineering applications. So this gives you a little bit of overview of the capabilities of ALD in general. ALD is not a new technique. As a matter of fact, the first patent was applied for in 1974. And this periodic table shows the materials that have been reported to be prepared by ALD. And you see that this periodic table is filling up over the years. Things will go quite quickly when we reach the 2000s. Just to point out how it works. So, for example, if you take titanium, you see that titanium oxide and titanium nitride has been deposited. Also, elemental titanium. That's by the gray square here, titanium sulfide, compounds of titanium with other elements, etc. So you see that when we reach 2022, that this periodic table has filled up quite nicely. So many processes have been reported. It does not mean that all these materials are very easy to make by ALD. Some of them are very easy, other ones might be somewhat more challenging. And if you want to find out whether a certain material has been prepared by ALD, I think this resource on atomic limits is very helpful. It's the so-called ALD database. And if you go to the website, you can click on this icon here, and then you will get you will get this periodic table, and then you can click on the elements and find out which materials have been deposited with that element in it. And we give the materials, we give the precursors, the precursor and the co-reactant, if you want to say so, but also the references. So there are direct links to publications. So everything that has been published should be traceable in that database. And in case you develop your own ALD process and you publish about it, then you can even add your, well, actually, I would encourage you to add your ALD process. We'll review it, and then we'll add it to the database so that other people can find it back too. Now, atomic layer, let me just go over some of the basics. So as said, you deposit films atomic layer by atomic layer, and you do this by repeating cycles. Here you see a cycle, and you repeat these cycles, and every cycle gives you an atomic layer, so a certain thickness. This slope of the line here, so would then be the growth per cycle. And every cycle consists of typically 2 half cycles. Let me show you some data. So this is some data on oxides, actually all plasma-assisted ALD oxides. And you see that you can really control the thickness very precisely by setting the number of cycles. Now, as said, the slope is what we call the growth per cycle, and that's a very important number. We call it also GPC. And this is typically in the order of 0.1 nanometer per cycle, but it varies. It varies for the different materials. It varies for the different materials. It also depends on the precursor and co-reactant that you use. I will come back to that in a second, and the substrate temperature. But other than that, it's a very reproducible number. So for certain conditions, for fixed conditions shown here, you will get the same growth per cycle from run to run, from day to day, from lab to lab. Doesn't matter where you are in the world, you should get the same number. So it's very reproducible as long as these conditions are fixed. And this is one of the key features of ALD. I'll show you here some precursors that you can use, or the precursors used for these materials. So it varies from relatively simple trimetal aluminum for aluminum oxide to this pretty complex precursor for titania. To make these turn these materials in an oxide, we use a co-reactant, and that can be water in many cases, but it can also be ozone or oxygen plasma. And when we use an oxygen plasma, then obviously we are talking about plasma-assisted ALD, and that's what we are talking about today. Okay, so then these half cycles, to go a little bit more into detail. So in this first half cycle, we expose the surface to a precursor that reacts with the surface in a self-limiting way. I'll come back to that in a minute. And then we purge. And then we do the co-reactant exposure, so water or oxygen plasma, for example, that reacts now with the surface groups that are left by the precursor, that reacts in a self-limiting way, and then we purge again. And here I show a particular, well, actually the prototypical example for aluminum oxide, where we see here that aluminum oxide, we use trimetal aluminum as a precursor. It reacts with OH surface groups, making volatile CH4, and then leaving on the surface aluminum oxygen CH3 groups. And then we do the second half cycle, so half cycle B, we introduce water, and now the water exchanges removes actually the CH3 and replaces that by OH, and making again CH4, and then leaving the surface OH covered again, and then we can carry out the next cycle. So, well, this is a very well-known ALD process. I think many of you are very much aware of this. And you keep on repeating this. What you do have to check, and what's very important to really find out whether it's an ALD process, you have to check the saturation curves, because what's important is that these surface reactions are self-limiting. So what we typically do, we vary the precursor exposure for fixed conditions otherwise, and then we see whether we have saturation for the precursor step, for the reactant step, and we also check whether we have saturation for the purge steps. And here I show some data. On the top here we have thermal ALD of aluminum oxide from trimetal aluminum and water. And as you see, it doesn't matter whether we dose the TMA for 20 seconds or 60 seconds, we do have this self-limiting behavior, and we have very clear saturation. The same thing holds for the water step, approximately. And also here, we see that the purge, if we have that long enough, then the growth per cycle is not affected. If we are too short, we get in a little bit of problem, because then we get CVD reactions. We don't want the water to meet the trimetal aluminum in the gas phase, because then we get the CVD reactions. Well, of course, that depends a little bit on the application, whether this is a problem, yes or no. But of course, if you're working under these conditions, you have no truly ALD, and you might not have some of the benefits that ALD would offer. And on the bottom here, we also see the plasma-enhanced ALD process using the same precursor, and now with oxygen plasma. Again, we see very clear saturation behavior for the precursor, also for the plasma step here, very nice saturation. And again, we see that the purge, certainly after the TMA, should be long enough. The purge after the oxygen plasma doesn't matter so much. So this is something that you always need to establish when you want to work with a true ALD process. Okay, so let me also show a animation. If it's not clear, this is an animation for the plasma-assisted ALD process. So this is a drawing of our home-built ALD reactor, and we're going to zoom in at the wafer level. And we see that the wafer is covered by OH groups. We expose this to the trimetal aluminum precursor. This will react now with the OH, replacing the OH by these surface groups. And this will happen everywhere at the surface. And then this reaction will stop. It's self-limiting. We purge. And then we introduce the oxygen plasma. So the oxygen plasma contains mostly atomic oxygen atoms. They react with the CH3. They basically burn the CH3 off in this particular case, leading to CO2 and water, and will replace the CH3 by OH groups. Again, this is self-limiting. We purge, and then we are ready to do the next cycle. So this is a very schematic way of how we do plasma-assisted ALD. Now, this animation might suggest that we deposit crystalline films. That's certainly not the case, certainly not for aluminum oxide. These films are always amorphous. In many other cases, we can also have polycrystalline films, of course, but they are not like crystalline as I showed in the animation. Well, just to summarize the processes that I've just shown, thermal ALD and then plasma-enhanced ALD, very similar apart from the co-reactant step. Here we use water and we make CH4 as a reaction product. For the plasma process, we use oxygen plasma, oxygen atoms, and they will mostly make CO2 and water as a reaction product. In both cases, we end up with OH covered surface. One other aspect is the temperature window. So let me go over that. So ALD typically works well within a certain temperature range. And that's what we call the temperature window. Now, often you read back that this temperature window is where the growth per cycle is constant. That's certainly not the case in many cases. It can also, the growth per cycle can decrease or increase with temperature, for example. The definition is really of the temperature window is really in the what's the range where you really have truly ALD reactions. So that's basically the definition. At some temperature, you might get, for example, precursor decomposition, and that will negatively affect your your growth. So then you're outside of the ALD window. At low temperatures, often you see that at some point the growth per cycle drops a lot, and you also don't get truly saturating behavior anymore. You get maybe other issues, and then you're also out of the temperature window. Now, generally speaking, the temperature window is typically extended to the lower temperature side when you do plasma-assisted ALD. So with plasma-assisted ALD, you can go to lower temperatures to prepare your films than with thermal ALD, generally speaking. There might always be exceptions. And here I show a very low temperature process. This is actually ALD of silicon oxide done at room temperature using this precursor. And here you see the saturation curves for the plasma assisted process. Actually very nice saturation, very short, relatively short cycle time for our reactor at least. And here I can also point out that if you use this precursor and you use water, you will not get any film growth at all under no conditions. If you use ozone, you can get film growth at higher temperatures, but apparently there was no film growth under these conditions with ozone at room temperature. So that really clearly shows the benefit of using a plasma. If you really need to make high quality silicon oxide at low temperatures, then you can do this with the plasma assisted process. Okay, one other important aspect coming back to this slide is the conformality. Let me also say a few more words about this. So why do we get such a good conformality and uniformity by ALD? Well, the reason is that ALD and plasma enhanced ALD is really a surface controlled process. And this is different from flux controlled processes, such as you typically have with PVD or PCVD, and also in many CVD cases. Well, if you have a flux controlled process, then your film growth is really depending on the flux. And if you would have a large wafer and you would have a point source, then I think it's obvious that your film growth is falling off here at the edge of the wafer. And if you would have this special 3D structure at your surface, then you can also see that the flux that you will get here is very low, and you will certainly not have a uniform or conformal film inside your 3D structure. It's flux controlled. The deposition rate is proportional to the flux. With ALD and also plasma enhanced ALD, that's not the case. You can get the same thickness, the same film thickness everywhere. The flux of species will be lower here, so you might have to wait a little bit longer before you reach saturation at this corner. So the saturation time will be dependent on the flux, but if you wait long enough, you will get as much material here as here before you do the next cycle, such that the thickness is not affected by the flux. So that's the difference. The flux is important for how fast you reach saturation, but if you wait long enough, maybe you need to work a little bit longer, wait a little bit longer if you have these complicated structures, then you will reach the same flux everywhere and you will have a conformal film everywhere. So that's the main, well, that's basically the difference between ALD and the flux control processes that are very well known. And this is an example. This is a nanolaminate of silicon oxide, titanium oxide, aluminum, and aluminum oxide. This is the TM image, and this is the EDX image of that. And you see that we can get a very conformal film stack by ALD. As a matter of fact, this is done by plasma-assisted ALD. So we can see that we can grow very conformal films by this plasma-assisted ALD process. Okay, maybe also interesting is that, so some history, very briefly, I mentioned already that the first patent was applied for ALD in 1974, so it's a long time back. Initially, there was not so much going on, there was little interest in ALD, but that really changed around the turn of the century. Obviously, because the people in the semiconductor industry became really interested in the method. They were facing some big challenges, and well, ALD appeared to them appeared as a solution to them, and actually it was a solution. So then ALD really took off, and now most of the applications you find in micro and nano electronics, and I'll come back to this later. The first report on plasma ALD was in 1991, but that was only one paper, and then the rest of the papers started appearing here in the early 2000s. It took a while also before plasma-assisted ALD took off, but now you see many reports on plasma-assisted ALD in the literature, and plasma-assisted ALD is used heavily also in industry. I'll come back to that later. So yeah, talking about plasma-assisted ALD, just to come back to the cartoon. So just to remind everybody, so plasma-assisted ALD is very similar to thermal ALD, but only the co-reactant step. Then you use a plasma, and this plasma can be different gases, or can be generated in different gases, such as hydrogen gas or nitrogen gas or oxygen gas, depending on whether you want to make an oxide or nitride or maybe a metal. Now, what are the merits for using a plasma? I mentioned a couple of them already, but let me just go over them. So you can have improved material quality, and you can have that under many conditions, but you can certainly have that at low temperatures. And in some cases, you cannot deposit the material with thermal ALD unless you use a plasma. And I've shown already the case of silicon oxide. There are also some materials that are very difficult to make with thermal ALD, or maybe just not possible. For example, silicon nitride is very difficult to make with thermal ALD, and their plasma really provides a solution. And there are more of these materials. In addition to that, you have a good control of film properties. You can also have increased growth rate, so the number of nanometers per unit of time, because plasma-assisted ALD can also be faster in some particular cases, certainly again when you decrease the temperature. And then if you have the plasma source, you have more versatility in general. You can do pre-treatment of surfaces, but you can also do plasma cleaning of your reactor, for example. So that can also be very, very helpful. Of course, there are some challenges as well, and I'll come back to this extensively later in terms, so the conformality can be limited. I will come back to this extensively, as I said. Also, you have to be careful with plasma-induced damage. You have to really know what you do and work under the right operating conditions. And the other thing is that when you use a plasma, you basically have some additional complexity because you need a plasma source. And, that is something that you have to take into account. It doesn't have to be very complicated, but of course, it requires some additional tool set. And that also points out that people only use plasma assisted ALD when there is really a clear benefit, right? If you can do the same thing with thermal ALD, then you could wonder why using a plasma, because you have this additional complexity. Although it's maybe not too difficult, but you can still wonder why you would use it. But there are many cases where ALD, plasma assisted ALD, is really giving some merits, and that's why it's also used in industry. Now, there are several review papers on plasma-assisted ALD. Two of them we wrote ourselves. I can recommend them. This was the early one in 2011. This was a follow-up paper in 2019. It's also open access. And I also like this paper a lot. This is by David Boris. So I can really recommend these review papers if you want to read more. And also, this is a very interesting website where you can also find some details about plasma-assisted ALD. It's Mark Soa is managing this website, and it's actually also a very nice resource. Okay, so next I would like to discuss some basics of processing plasmas. Some things that you have to know when you work with plasmas, I think, or which is very wise to know when you work with plasmas. So what is a plasma? So first of all, a plasma is a gas that has free charged particles, electrons and ions. So that's important. That defines a plasma, that you have free electrons and free ions. There are also other species in the plasma, for example, atoms, and some of these species can be reactive or excited molecules or reactive molecule fragments, and that's what we often call radicals. Radicals are reactive species that are neutral. Another aspect of plasmas is that it emits radiation, and we already saw some fancy images. Now, a plasma is typically quasi-neutral. That means that the electron density and the ion density are equal to each other at macroscopic length scales. Typically beyond a millimeter, then the electron and ion density are equal to each other. Processing plasmas that I will be talking about, they have typically a relatively low ionization degree in the order of 10⁻⁶, 10⁻⁴. So we have mostly neutrals, but a few, well, a low fraction of that is ionized. Another very important aspect is that the electrons in the plasma, we heat them by electrical fields. In man-made plasmas and processing plasmas, we heat the electrons by electrical fields, and they are hot. They are about, we talk about electron temperatures, and they are about 30,000 K. So this is about 3 eV. At the same time, the gas temperature is typically low because we work under relatively low pressures in the order of torr or millitorrs. And then the gas temperature can remain very low, 300 to 500 kelvins. And that really means that we work under non-equilibrium conditions. And that's the very important aspect, because that's also what we want to. We want to heat the electrons. We don't want to heat the gas, because the gas would heat up the substrate, and we want the substrate to work under, to stay relatively cool, certainly not going up to very high temperatures. And that's a very, very important aspect of plasmas. We heat the gas, we heat the electrons. The electrons will dissociate the gas, they will ionize the gas, but without heating the gas, and then we can modify or deposit a material by the plasma. Well, the electron temperature and electron density are very important parameters. So this is a plot that you often see, where you can see all the different plasmas that exist. Some very dense and hot plasmas, like the sun. Also some very cold plasmas or relatively cold plasmas with low electron densities. But we will be talking about these industrial plasmas, man-made plasmas, where we are in this range. We work under non-equilibrium conditions. The electrons, they are typically in thermal equilibrium, and that means that we describe them, that we often can describe them by an electron energy distribution function, which is Maxwellian, in a pretty good approximation. So the electrons, they are in thermal equilibrium with themselves, maybe not with the other species, but they are in thermal equilibrium with themselves. And that means that we usually have an energy distribution shown like here. This is a logarithmic plot. That means that we have a variety of electron energies. So for a given TE, we have a variety of electron energies. We have some electrons which are relatively cold, but then we also have some electrons that are relatively hot. And it's described by these equations, either the velocity distribution function or the energy distribution function. Well, why is this important? Well, these hot electrons, only these hot electrons can ionize and dissociate the gas species. So you see here the electron energy distribution function again. And then you see here the electrons that have an energy higher than 10 eV approximately. And this is what you typically need for excitation of argon or ionization of argon, or for example, for dissociation of nitrogen or ionization of nitrogen, you need these threshold energies, and that's where you need these hot electrons for. So most of the electrons cannot do these inelastic collisions. These are inelastic collisions. Most of the electrons cannot do this. So we have a fairly low ionization degree. And then of all these electrons, only a few of them can do this ionization and dissociation reactions. So collisions with hot electrons in the high energy tail, they are responsible for ionization and dissociation. I explained this basically already, but let me show it once more in this plot. So what we want to do is work on the non-equilibrium conditions with processing plasmas. And that's why we work typically at low pressures, in the order of a torr or less. And then we heat the electrons, but we don't heat the gas. The electrons are in thermal equilibrium. They have a lot of collisions with themselves, mostly elastic collisions. But the collisions between electrons and the gas phase species and ions are infrequent, and also the collisions, there is only a very small energy transfer. Electrons have a hard time transferring the energy to the heavy particles because of the difference of mass, and that ensures that we can have these hot electrons and that we have these cold gas phase species, and that explains this temperature difference. If we go to high pressures, for example, to an atmosphere, then things change. Then the energy transfer is still very poor, but then we have so many collisions that everything gets to about the same temperature. And then we talk about thermal plasmas. But with processing plasmas, we typically want to work under these conditions, so that the substrate can remain at low temperature. Another very important aspect is also plasma sheet formation, because that explains ion bombardment. So I would like to explain this with this slide. So if you expose a floating substrate not connected to anything to a plasma, then the electron current density would be much higher than the electron current density. And the reason is that the electrons are much lighter. So their flux would be much higher than the ions. But if this substrate would be floating, that is not a sustainable situation, because we cannot charge up this floating substrate forever. So what will happen in steady state conditions is the formation of a plasma sheet. And this is a space charge region that is very close to the substrate that now shields the electrons from that substrate and accelerates the ions. And that's what we call the plasma sheet. And over this plasma sheet, the space charge region, there will be a potential drop. And this potential drop is responsible for the fact that ions are accelerated to the substrate and become energetic. And the flux becomes directional. So if you have heard about ion bombardment, it's because of this plasma sheet that develops very close to the substrate. The sheet thickness is in the order of maybe a millimeter, as you can see here, and that is responsible for the ion bombardment. The ions inside the plasma, they have a low temperature, as I explained before, so they have a low thermal energy. But once they get close to the substrate, they will be accelerated, and they can become energetic and they can become directional. And this is an example of an ion energy distribution function that we have measured for various plasmas. And you see here, for this particular plasma condition, we had ions with an energy of about 30 electron volts, which is an energy way higher than the thermal energy. Here I show the ion angular distribution function to point out that the ions come into the surface quite perpendicular to the substrate. There's a little bit of variation due to the thermal energy that I already have, but most of the ions come in around a few degrees angle. When you increase the pressure, that will widen a little bit because of collisions that you can have in the plasma sheet. And that's what I would like to explain with this slide. So the sheet thickness is typically a millimeter, for example, and the sheet thickness will wrap around the substrate. So if that would be a curved substrate, the sheet would wrap around that. But if you have trenches with a small feature size, suppose 100 nanometer or something like that, or maybe a micron, then the sheet would not fit in, the sheet would not be affected. And that means that the ions would come in perpendicular to the substrate also here at the bottom of this trench. So microscopic features, the sheet is not affected and the ions hit mostly the bottom of the via or trench. And this is something that we use a lot in plasma etching, to etch these features. What's important is to also check whether the ions, whether they have collisions in the sheet, yes or no. And that defines whether the sheet is collisionless or collisional. And this will depend on the pressure of the plasma. So if the pressure is increased, then at some point these ions will start colliding with neutrals. And that happens when you increase the pressure. And then the ion angular distribution will start to be a little bit wider. It's still pretty peaked here, but that depends on the sheet thickness versus the ion mean free path. So that's another aspect to take into account. Then I showed already that plasmas emit radiation. That's what you can see here. This is our home built system. This is the ICP source. This is the downstream region, and we can see emission in the visible, but we also see emission in the UV, especially in the vacuum UV region. And I will come back to that later because that's something to take into account. This is the plasma composition, for example, on oxygen, just to give that as an example. So this is the gas density of oxygen neutrals. As said, the ionization degree is relatively low, as you can see here. So that's in the order of 10⁻⁵. I mentioned that earlier. But what is most important in the plasma are the radicals. And these are oxygen atoms in this particular case. And they have, the dissociation degree is typically up to a few percent. In terms of surface chemistry, the radicals are most important. That does not mean that you can neglect the ions, because the ions can have energy, as I just explained. But the radicals will be most dominant in the surface chemistry. And here I show some additional information on the ions and the electrons for this particular plasma case. So here we have measured the electron density, for example, just above the substrate. So here you see some typical numbers. Electron density and ion density, they are equal to each other. The ion flux, the electron temperature, typically 3 eV, and also the ion energy. And these are some key parameters that are good to know when you're working with plasmas. Of course, many people don't have the opportunity to measure these, but they are important plasma properties. And to really understand what's going on at the surface, you might want to have a good understanding of these parameters, either measure them yourselves or have a look in literature what typical numbers would be. And I will come back later when we talk about the fundamentals. I will refer to these numbers extensively. The plasma radiation that is created by, for example, electron collisions. When you have an electron collision with oxygen, it can dissociate the oxygen. This is an inelastic collision, so you need quite energetic electrons for this. And then the oxygen can be electronically excited, and then it can fall back to the ground state and emitting a photon. And this can be in the visible. You see here the visible photons, but it can also be in the UV or VUV region. And these photons are pretty energetic, as you can see here. And that's something to take into account because they could affect the material that you are depositing. This is just an overview of different plasmas that you can use. Argon is typically not used for plasma-assisted ALD, but hydrogen plasmas are, nitrogen plasmas, oxygen plasmas, and there are a variety of other plasmas that you can use as well. Ammonia plasmas, water plasmas, etc. And here you also see the plasma radiation of a hydrogen plasma and the nitrogen plasma. You see the visible region, but you see in these cases, there was also emission in the UV and in the VUV, and that's something not to neglect. And this is another figure to point out the ion flux and the ion energy, just the same thing as I showed before. Typically ion fluxes, that's what you would like to know, because the ions can also affect the material, and also you would like to know the ion energy. So this is just the similar thing that I've shown already before. Okay, now to wrap up this first part, I think this is a kind of an interesting plot. This would be typical in noble gas plasma and argon plasma. Just to reiterate, we have argon gas, then the ions and electrons that are way lower density. The ionization degree is small. The electrons are way hotter than the ions and the gas. The gases and the ions are relatively cold. The electrons are the species that we heat, and the electrons, they exchange their energy very poorly with the ions and the gas-phase species, and that's why they can remain relatively cold. In this sheet, we will accelerate the ions, and that will lead to ions that are energetic, that are quite energetic, and they can really bombard the surface. And that's something that we can exploit or that we can try to avoid, maybe depending on the application. This is the deposition plasma, for example, oxygen plasma for plasma-assisted ALD. It's very similar to this case, but now we also have free radicals, oxygen atoms, for example, and their dissociation degree is typically in the order of 1%, depending on the plasma conditions, of course, but for the rest, it's very similar to the argon plasma. Okay, so this summarizes what are the key properties of processing plasmas, and this is also why we like to use the plasmas in ALD. So first of all, we create reactive species in the gas phase, so we can control the reactivity in the gas phase without having to heat the substrate a lot, for example. So that's a very important aspect. And we can work with species that are maybe not too reactive. Normally, we can make them reactive by striking the plasma. We can work with a relatively low heat flux. We heat the electrons once more. We don't heat the gas, so the gas stays cold and the substrate stays cold while having this high reactivity. And then under certain conditions, it's interesting that we also have ions that hit the surface. They can lead to ion bombardment. That's something that can have a beneficial effect in some cases. It can also have a detrimental effect if you don't do it right. But it is something that to exploit. And well, the flux of ions is anisotropic, so that's also something that you can use in some cases. And I like this sentence that summarizes it all. Plasmas can deliver a high, diverse, but selective reactivity to a surface without heat, and therefore you can access a parameter space in materials processing, which is unattainable with strictly chemical methods. Yeah, so you can do a lot with thermal ALD, but in some cases you can just do more with plasma-assisted ALD. I thought also it's good to, that wraps up the first part, the basics of ALD and processing plasmas. These are the takeaway messages. Plasma-assisted ALD can have several merits over thermal ALD, depending on your application, of course, because there was also some things that you have to take into account, challenges and complexity. And these, if you understand these, then you also have a pretty good understanding why a plasma can be very helpful for your process. Okay, that brings me to the end of this first part. Maybe we can have a look a little bit on the questions, but I need a little bit of time just to see what the questions are. So I see first a question about plasma-induced damage. I will come back to this later in the third part. Then there was a question about the plasma. Is that applied to the precursor or the co-reactant or both? So in plasma-assisted ALD, the co-reactant only the co-react, we only use a plasma during the co-reactant step. So we don't use the plasma during the precursor step. So the plasma is only used during the co-reactant step. Okay, maybe people come up with other configurations as well, but I think in more than 99% of the cases this is true. There is also an example about nitride. Maybe I'll come back to that later. There was a question about how to be sure there is a monolayer in a half cycle A. So as a matter of fact, you deposit less than a monolayer by an ALD cycle. So by a complete ALD cycle, you deposit less than a monolayer. So the cartoons are sometimes a little bit misleading, but I always talk about atomic layer by atomic layer, because you deposit less than a monolayer in an ALD cycle. So that's one thing that I would like to point out. The other thing that I would like to point out is that, how to be sure that it was less than a monolayer. This depends on the surface chemistry. So if you develop an ALD process, you have to test it, whether it is self-limiting. And if it's self-limiting, then you have an ALD process. So there is no way that you can just take two precursors or a precursor and a co-reactant and say, oh, this will be an ALD process. And that will be a self-limiting process. You have to rely on the surface chemistry. And if you test a precursor combination with a co-reactant, then you have to find out whether it's self-limiting and whether you deposit an atomic layer per every cycle. And what makes it self-limiting? Well, that is depending on the surface chemistry. So you very much rely on the surface chemistry. If there are, sometimes people would like to deposit a certain material by ALD, and then you have to look for a chemistry that is self-limiting. And there is no guarantee that you'll find one. But if you look at the ALD database, you see you find a lot of ALD processes already. So that's usually a good starting point. Okay. Then yeah, so I see one question I don't completely understand, but there is also a question, how do you control the chemistry from the very first layer to the subsequent layer? That's actually a very good question. I have been talking about ALD really in the steady state case. In the initial case, when you work on a fresh substrate, you have basically hetero deposition. So you deposit maybe aluminum oxide on a silicon wafer, and then initially the growth will be on silicon oxide, for example. And then all kind of effects happen. We call that initial growth. There is a whole field within ALD actually that looks at that. So I have skipped over this for the moment. Maybe I'll come back to that later. Initial growth is not trivial always, but in some cases it is. Aluminum oxide grows on almost everything, but there are also materials that don't grow easily on other materials. But this is a very good question, but I have skipped over this a little bit. Plasma-assisted ALD works easier on any substrate than thermal ALD because you're less relying on the surface chemistry. You force the surface chemistry a little bit more with the plasma. So that's maybe a thing I can say here. And then let me see, there was also the GPC. Well, I'm not completely sure what the question is. Maybe that can be more specific later. The GPC.
Is that the anonymous attendee's question about the GPC?
Anami is questioning about the GPC. So,
Nash, if you can clarify your question a little bit, that would be helpful. Thank you.
And otherwise, we can maybe come back to that in the next part. maybe that question could be clarified a little bit. I think it's maybe time now to first have a 10-minute break, and then I will continue about in the next about the ALD equipment, the plasma assisted ALD equipment.
All
So
right.
let's have a 10-minute break.
Yep. All right. I'll bring everybody back at 10 minutes past the hour. I know many of you are in different time zones, so we'll just come back at 10 minutes past the hour. I do use my cell phone as my time frame, so I'll bring you all back in. Erwin, there are several questions. If you've answered them, because they kind of went out of order, if you can mark them as answered live and done for me, that way I know which ones you've actually answered, and then leave the other ones open for yourself for later.
Yes, I
we'll
will
come
do
back.
it.
Okay, thank you very much. We'll see everybody back at 10 minutes after the hour. I'm just going to share some slides. Thank you. All righty, we've reached 10 minutes past the hour. Erwin, it looks like you're ready to begin if you want to unmute and share your screen. It looks like there's quite a bit more questions, but let's take a few and see if they fit into that section that you've covered or if they're leading into your next sections, okay?
Okay, well, thank you, Heather. Well, I saw there are lots of questions, which is very much appreciated. Also, some very good questions. I think some of those will be answered in the next session. So I propose that we just get started, and I'll try to make sure that those questions will be answered. And otherwise, we can do it later, or we can do it even offline. I can come back to some of those.
Okay.
Well, I would like to continue now next with the plasma-assisted ALD equipment, because that's, of course, very important. And okay, there we go. So if you develop a process, you have to make several choices. And that's, of course, good to realize. So first of all, you have to select a precursor. And depending on the material that you want to make, there's a variety of precursors that you can choose. The choice of precursor is always very important for ALD. And then next, you have to choose a co-reactant. And this co-reactant can just be a gas like water or ammonia, or a gas that has been like ozone, that is reactive. With an ozone generator, of course, you can also use a plasma, and that's what we're talking about. And there are a variety of plasmas, as you can see here, that you can use. You also have a variety of ALD cycles. So far, we have been talking about AB type of ALD cycles. In the fourth block, I will try to talk about. I hope I will talk about advanced ALD cycles, where we do, for example, ABC type cycles, or where you even use supercycles. For example, the nanolaminates that I showed before, you can define them as supercycles. You also have a choice of ALD reactors. We distinguish typically temporal ALD, where you do the ALD cycles as a function of time, and that can be a flow type, thermal ALD reactor, or a showerhead ALD reactor, batch type, or we can use plasma assisted ALD reactors, and we'll come back to that in a minute. We can also do spatial ALD. I will also show that, because there you can also use plasmas. And then some people are even doing ALD on particles, so that's another field. And then you have to choose your process conditions, your temperature, your doses, what is the exposure of the precursor and of the co-reactant, the purge times, the pressure, etc. And they all matter, of course, and they certainly matter when you do plasma-assisted ALD. So, in terms of reactors, we usually distinguish three main classes of plasma ALD reactor configurations on a high level. So, one type is what we call direct plasma, and this is often a parallel plate reactor with two electrodes. And then the substrate is positioned on one electrode. And that can be on the grounded electrode, but it can also be on a driven electrode. So this is the plasma source, the plasma generator. And a direct plasma means that the substrate is involved in plasma generation. So here, the substrate is on the grounded electrode, but that substrate, this electrode, is involved in the plasma generation. And that means also that the plasma generation itself is affected by the substrate conditions and vice versa. So that's a direct plasma. In a remote plasma, typically we have the plasma generation upstream of the substrate. For example, you have a plasma source here on a chamber, and then here's the substrate. That does not mean that there is no plasma above the substrate. There can be still active plasma here. But the substrate is not really affecting the plasma generation. So if I heat the substrate, for example, the plasma is not affected. The plasma generation is not affected. And then the third example is what we call radical enhanced ALD. So that's, for example, with a remote plasma, but that is very far put very far away from the substrate. For example, as shown in this particular case. And then many of the plasma species might not survive. They might not survive when they reach the plasma, when they reach the substrate. For example, ions and electrons that might recombine before they reach here. And that will usually typically decrease the flux of reactive species, and therefore the reactivity will be decreased. But on the other hand, yeah, maybe it also works well depending on your application. So these are the three main classes. Now, here you see actually a variety of plasma ALD reactor concepts, and I will go into detail in a bit. But we have a variety of plasma ALD configurations. We have a variety of plasma sources. For example, here, these are all remote plasma sources, but they're all different kind of sources. We distinguish temporal ALD and spatial ALD. We can use different substrates, wafer type, or maybe flexible foils, or even particles. And then there is a large variety in operating conditions. This is a table that that was published in our review paper. And it gives you a little bit of an overview of what kind of plasma sources are used by which companies under which conditions. I would like to emphasize that, for example, capacitively coupled plasmas, I will come back to that in a minute. These are direct plasmas. They're often used by companies that build equipment for high volume manufacturing. So these are the typical tools that are used in high volume manufacturing. Inductively coupled plasmas or other types of remote plasmas, they are often used for more research applications. Sometimes also for production, but also certainly also for research applications. And that's because they're usually typically more flexible. And then with spatial ALD, these are spatial ALD systems working at low pressure. And these are also used for high volume manufacturing. And then there are some other spatial ALD cases which are much more research-like, where the method is still being researched. Well, that gives you a little bit of an overview. So first of all, a few words now on temporal ALD systems, and then also the wafer type. That does not mean that you cannot use other substrates here, but these are typically what we call wafer type systems. So I mentioned already the capacitively coupled plasma is very popular in industry, and it basically has two electrodes separated with a certain distance from each other, and then you create the plasma in between. And the substrate is involved in plasma generation. The power generator is often 13.56 megahertz, but it can be lower frequencies or even higher frequencies. There is a possibility to add a mesh in the plasma zone, and I will come back to that later. Then you can make this plasma a little bit more remote, but otherwise it's a direct plasma if the mesh is not there. Now this is a so-called ICP plasma. It's an inductively coupled plasma where there is a coil wrapped around a tube, or there is a coil put on a planar dielectric window. So the coil is basically not touching the plasma itself. There's always a dielectric in between. And this is what we often, what we also label as a remote plasma. The frequency is also typically 13.56 megahertz radio frequency. And here you have the option to bias the substrate by an additional power supply, and then we can control the ion energy. And that I will also come back about that later. And I saw there were some questions about that. This is the so-called hollow cathode source. I will come back to that later, but you can also add it as a remote plasma source here. And this is a microwave source, and that works. This works also at 13.56 megahertz, and this works at microwave frequencies. So capacitively coupled plasma is a direct plasma. Here you see typical operator conditions. just for your reference. For ALD, people use typically pressures around the Torr. So they are at a higher plasma pressure. And that means that, for example, ion energies are reduced. The ion energy is not that high. An ICP source, but also some of the other sources, they also often called high density plasma sources. And that points out the difference between these sources and capacitively coupled plasma sources, because here the ion and electron density is way higher than for the CCP plasma. These plasma sources can also be operated, or are often operated, at lower pressures. And here also you see some differences in the electron energy distribution. For example, this is a very nicely Maxwellian distribution for a ICP reactor. And this is, for example, the case for a CCP reactor, where you have a low electron temperature, but you have a very high electron energy tail. And that depends, of course, on the operating conditions. Once more, only these energetic electrons, they can do the elastic collisions that lead to ionization or dissociation. Talking about direct plasmas, 2 electrodes, and the ion energy at the electrode is very important, or can be very important. And in this particular case, it will vary with the type of electrode, whether it's grounded, the grounded electrode, or when it's driven. This is a grounded electrode, and then you see here that the ion energy, so this is again the ion energy distribution function. The ion energy is fairly low, it's up to 30 eV here, and it depends on the pressure. So if you increase the pressure, you see that the ion energy drops. This is due to the collisions in the plasma sheet. The powered electrode here, you see that you go to way higher ion energies. And this is really high. And that's often you would like to avoid that with plasma-assisted ALD. And again, you see that if you increase the pressure, the ion energy will drop. So that's a good thing. Now, it looks like symmetric, but this case is not very symmetric, because this is grounded, and also the walls, the walls of the chamber are also grounded. And that makes this voltage asymmetry. So the grounded electrode is low voltages, low ion energies. The powered electrode is high voltages. So that's a particular configuration. If you now go to more industrial type of reactors, then they use typically big wafers, and then the system becomes more symmetric. And the ion energy distribution for the driven electrode is pretty similar to the one for the grounded electrode, because of the fact that this case is much more symmetric than the earlier case. Again, here you see the influence of the pressure. At very low pressures, we can have very high ion energies, but when we increase the pressure, then the ion energy drops. And as said, with ALD, we typically use very high pressure, so the ion energy will not be that high. So that's an important aspect. If you talk about CCP reactors, then people also talk often about alpha mode and gamma mode. This is the operation mode depends on the pressure, mostly. The gamma mode is typically at very low pressures. Then you have also ionization by secondary electrons. But that's what you try to avoid typically with plasma-assisted ALD. You like to work at higher pressures, because then the ion energy is lower, but also the uniformity will be better. So that's typically why people work at higher pressures. I mentioned already that you can do the CCP with or without grid. So this is the normal operation. I think all the industrial high volume manufacturing applications, they use without a grid. But this is pretty interesting from a research point of view, that you can put a grid in between. And the grid would confine the plasma between this grid, which is grounded or can be even driven, and this driven electrode. And now you would have, in this region, you would have still the plasma generation. So the RF E field heats the electrons, where you can choose between alpha and gamma mode. But here, under the grid, You will still have plasma, but you have no RF field. So then the electrode temperature will decrease, and you basically have you have no active plasma species, or not very active plasma species anymore. And that will that can be helpful, because then you might reduce the ion energy, for example. So this is a configuration that you find back in some particular cases. I will show a manufacturer or that sells this option. The other thing that you should wonder about, or at least I wonder about, whether this is really a robust solution, because this grid can quite easily be damaged also by the plasma, because you get maybe shorts. So that's maybe another thing to take into account. Then a few words about ICP reactors. I showed this figure already earlier. This was that was for this ICP reactor that I introduced. So so here the ion energy was measured here at the substrate level. You see it depends on the plasma, and you also see the ion flux. Now this ICP mode, what is important to know there, I think, if you read literature also, is that you can derive this under two conditions. You can have the E mode or the H mode. The H mode is really the real ICP mode. Then you have real inductively coupling. And then you get a very, very bright plasma. And all the benefits that an inductively coupled plasma has. However, in many cases, you also have some capacitive coupling, and that capacitive coupling really takes over at lower powers. And I think many papers in literature, they are operating the plasma in the E mode. And then you have capacitively coupling. That's maybe not directly affecting your film growth, depending a little bit on the application, but it can, because then you will have also some effects of capacitively coupling, and then you can I will show later, then you can have, for example, a little bit more erosion of the plasma source. So this is, I think, an important aspect to realize when you work with ICP plasmas. And actually, this is about the tube erosion. So here you see two plasma sources. This was for of a Vico Fiji system, a quartz tube and an aluminum tube, and then you have the coil wrapped around it. And people did some studies of tinitride, and they used different gases, and they used the different tubes. And one thing was that they found that the resistivity is worse when you use a quartz tube. And when you use a quartz tube, there's usually more oxygen in the film. And this oxygen then is leading to a higher resistivity. Now, it turned out, or actually it's pretty logical, but they have demonstrated it very nicely, that if you use a quartz tube and you generate a plasma in that, and you have some capacitive coupling, then you will have ion energy bombarding that tube, and then you can sputter away your tube material. And sputter yields, this is for argon, you can find similar numbers for other plasmas. The sputter yield for silicon oxide, quartz, is higher than for alumina. So that means that you will end up with more oxygen contamination, even in your metal nitride film, if you use, for example, a quartz tube. So this is something to know if you are, for example, having issues with your with oxygen contamination, and you work with a quartz ICP tube. Well, then the source would be this tube. And I always recommend to use alumina tubes and not quartz tubes. I think this was a nice study illustrating that. Another plasma source that gets a lot of attention is the so-called hollow cathode plasma source. This is somewhat similar to a planar electrode as you have in a CCP plasma. But this configuration can be put also far away from the substrate, and therefore act as a remote plasma source. And there was a company called Miglo that are selling these sources. You can fit them on our ALD reactor, maybe with some adjustments. The interesting thing here is that this plasma source, I will show that in the next slide, leads typically to higher electron densities, higher electron and ion densities. So you create more reactivity with this plasma. And that means that you can maybe speed up your process a little bit more because you just make more plasma with this source. Well, there was quite a lot of literature on this, and it's actually a pretty complicated source if you really want to understand it. So here you see some simulations. The electron temperature is relatively low, but then you have this very high energy tail. So these are electrons that are really, really hot. So that's one thing that you have to take into account. And the other thing is the fact that you have this high electron density and ion density in the plasma is because of these little holes in the cathode. There you will basically confine your electrons. The electrons will be confined in one dimension here between the two plasma sheets. And therefore you will increase the electron density because the electrons cannot easily escape. So that's the reason why you get this higher electron densities. Okay, so now let me show you some examples. So this is, let me first of all point out that these CCP tools that are used by the bigger companies for high volume manufacturing, these companies usually don't provide too much information, at least not on the websites about the tools. So I cannot comment too much on this, but I think they are pretty straightforward systems, as I showed earlier. The R&D systems, they are usually give a little bit more information, so I can say a little bit more about this. And this is an example of a CCP plasma by Bannock. So this is a standalone system, and this is in a cluster tool. And here you have the two electrodes, and they provide the option to use this grid. So by applying this grid, it's optional. You can put it in or you can take it out. You can actually make this system a little bit more remote or have it really as a direct system, direct plasma. This is another commercial tool, Picosun. Picosun uses this remote plasma source. It's actually a commercial source from Advanced Energy. And it's basically an inductively coupled plasma. So coil with around a dielectric tube. The distance between the coil and the substrate is very high. So that's one thing to take into account. They often say, okay, that we will use is maybe plasma damage, but of course you will use also the electron or the ion and radical flux a lot. So they usually operate as plasma source at several kilowatts, while other companies might do maybe even only 100 or 500 watts or something like that. So you have to run it at high powers to really get high reactivity here at the substrate level. This is such a system with a regular ICP source. This is the Vico Fiji system. So here the plasma source, this is the matching network. So this is the plasma source. They do also provide substrate biasing. I will come back to that. And here you see a case where this plasma source, the ICP source, was replaced by a holocathode source by Miglo. So you can just fit it on your system and then you can test that plasma source. That's just an example. KJ Lesker, they also have a system. It's actually also a very similar ICP plasma that they have, as you see here. So that's very similar as the Vico system. And another system that is pretty, well, actually, this is not so similar. It's also an ICP source, but this is the Centex Lyo system. They use an ICP source, but now it's a planar coil, or more an antenna, on top of a dielectric window. So then you can also make an inductively coupled plasma. And they also provide the option to do substrate biasing, as you can see here. And then there is the Oxford Instruments system. So the Oxford Instruments Flexal system, it has an ICP source, very similar to the Fiji and the Centec tool. And this is a new system that they have, and this is what they call a remote CCP reactor. So this is again the system that I showed earlier. And this has now, it's a CCP source, but you make the plasma between grounded electrode and a driven electrode here on the top. So this bottom electrode doesn't really play a role in that. And then the plasma is generated here. And then you avoid actually the use of a coil, whether the quartz or alumina tube, because it's all metal inside. So that's a new source. And this is supposed to have a higher productivity than the ICP source. I'm not sure I mentioned already, but there's also you can do substrate biasing, and I will show later results that we have obtained with this system. So as a matter of fact, here you see this Oxford Instrument source. We do have those systems in the lab. So this just gives you an image of how these systems will look in reality in a lab environment, in a clean room environment. So here is the ICP source on the top, then the chamber is right here. And then here you have the precursor cabinet, for example. And we also always fit a lot of diagnostics on our tools, optical emission spectroscopy, mass spectrometry, spectroscopy. I showed already some results that are very helpful for do process development, and that's why actually these remote plasma sources, you can much more easily do this, and that's why these remote plasma sources are very helpful for R&D environments. Typically, the remote plasma sources can easily do 200 millimeter wafers, or maybe even bigger, even bigger. Depends on the supplier whether they make them, yes or no. So I mentioned already substrate biasing. And I think there were some questions earlier in the Q&A about how can you control the ion energy. I will certainly come back to this quite extensively, but this is in remote plasma source, it's quite easy to add a second power supply to the electrode. And then you can apply additional power, and you can increase the ion energy. So this is the ion energy distribution function for a grounded substrate. And if I put a little bit of power here, this power is only used to accelerate the ions. So it's not used to create additional plasma, but it's only used to accelerate the ions. And then you see here, then you can get additional ion energy. And that can be helpful maybe for some of your processes. Now, several companies are offering this RF substrate biasing, Vico, Centech, and Oxford Instruments, and maybe even more nowadays. Let me show also this animation. This is an animation where we can point out two things. So this is some of our research that we are doing. So this is really about ion energy control. So if you have a grounded substrate, well, then you have still energetic ions, but their energy is relatively low. Then our other possibility is RF biasing. RF biasing, you use a radio frequency waveform, and that radio frequency waveform will make the sheet growing and decreasing in size. So, okay, we still have the grounded case here. Okay, now we are going to apply the radio frequency case. So then the sheet will move up and down, and then this is why you get this bimodal distribution. And now some new developments by several companies, I think, is to also apply a different waveform, a tailored waveform, and then you can control the ion energy much more precise and keep it basically constant during the large part of the cycle, and you only have a very short moment where you draw the electrons. So this is a development that's going on, I think, at several companies, and you find some information in on the website. Okay, next about spatial ALD. So spatial ALD, you have several systems. You have wafer type systems, but also other systems where you can either do wafers or flexible foils. So let me just point out that spatial ALD, you don't carry out the cycle as a function of time, but you carry it out as a function of position. And I will show you another animation to illustrate this. So this is temporal ALD. So we have a wafer which is static, and you pulse the precursor, the purge, and the co-reactant. and you do this as a function of time. And that's how you build up your film. So the wafer static, and you do this in one zone, one chamber. In spatial ALD, you keep the injection of the precursor and co-reactant and purge static, but now you move the wafer through the different zones. So the wafer is moving relative to the injection zones, and this is how you build up the film. So here you vary the position. And there are several configurations. One is, for example, where you have a rotating holder where you can add maybe several wafers, and then you rotate the wafers through the different zones. So here you would, this is a TEL system, the NT333, and then you rotate the wafer to a zone where you add the precursor, nickel in this case. Then you have a zone where you purge nitrogen, and then you have the plasma zone, and then you have the nitrogen again, and you have the precursor. So you rotate these wafers. And this is really used to increase the productivity, to really go to high volume manufacturing. And there are applications where this is really important, where cost is so important, and where you can tolerate also such a process. I'll come back to that later in terms of applications. There are other companies that they increase the productivity in other ways. So they don't use this spatial system, but they just have a multi-single wafer reactors. So these are basically one chamber where you have four wafers at the same time, and then they have that 4 times. So that's another approach. But you see in the literature, or that the companies are choosing either for this configuration or for that configuration to increase the productivity. This is another example of spatial ALD. This is the example of Lotus Applied Technology. So they have a system here. They have, again, this carousel, basically, where they inject the precursor here, purge, plasma, purge, etc. And they license the technology to Benec, that also sells a commercial system like that. I mentioned already the TEL system. Also, Yusung has a system, and I think also Applied Materials has the Olympia system, which are very similar to these systems for high volume manufacturing. And in this case, I mean, you don't have to use a plasma, but often a plasma is used. This is just a configuration where you can also do roll-to-roll ALD, which is maybe finding application soon. So this would be without plasma, so thermal ALD. So then you might have a foil, and then you could in this region you could do the precursor inlet, and then the reactant inlet. This is where they have now precursor here and precursor there, and then they generate a plasma in between. So that is another creative solution. I'm not sure whether this is this particular configuration works very well, but it shows what you can do. This is another configuration where you work at atmospheric plasmas. So then you need to use a plasma source that can work at these pressures. And there is a particular plasma that's called surface dielectric barrier discharge. And then you can work at high pressures. And you see here, this is the plasma source. It's basically a dielectric with here one electrode, and then the other electrode is right here. In this little gap, you create a plasma between this electrode and that electrode with the dielectric in between, and the plasma is flowing here to the substrate. And the substrate is moved underneath this plasma source. So then this would be the plasma region, this would be the precursor region, and the wafer holder is basically rotating, like in the other systems. Well, that gives you a little bit of an impression of the ALD systems, plasma ALD systems. I mentioned already that the R&D systems, you can also equip them with analytical techniques. I just want to point that out. It's not so much the topic of today's presentation, but these remote systems are very well suited, for example, for adding spectroscopy lipsometry. but also other methods was quartz crystal microbalance, mass spectrometry, infrared spectroscopy is a helpful tool, emission spectroscopy. So that's very easy to do in these remote systems. It will be a little bit harder in the direct plasma systems. Another topic that I would like to point out is impurities, because that's often where people, where people find problems. There is an interest in making, for example, nitrides by ALD, conductive nitrides. And this can be done, and people have reported about this. And here you see a non-comprehensive overview of some of the materials, nitrides, that have been deposited by ALD, by plasma-enhanced ALD, using various precursors. And here you see the plasmas. But if you look at the film composition, people often report a pretty high oxygen content. And depending on the application, you might not like this. And this is hardly a pure nitride anymore. 2% is maybe okay, but the oxygen will affect your film properties. They will decrease the conductivity. And there are several sources where the oxygen impurities can come from. One thing is that you can have post-deposition oxidation. You take your wafer out after ALD, you take it in the atmosphere, and it might oxidize a little. That's certainly an effect. You can have, of course, impurities in your precursor and in your plasma gas. So that's another thing to check. You have to work with high purity chemicals. The plasma source can be a source of oxygen. I showed already the case where we had a quartz ICP tube, where the contamination of oxygen was higher than with a sapphire, aluminum oxide quartz tube, ICP tube. But there was one more other thing that I would like you to be aware of, and that's the vacuum system itself. The vacuum system itself is also very important. And maybe in many cases, this is the most important aspect. And what is important to realize here, that the systems, the ALD reactors, typically don't work at low base pressures. So the commercial systems that are sold, they don't have very low base pressures. They often use O-rings and not metal gaskets, and they use maybe a roughening pump only. In some cases also a turbo pump, but they don't use the same vacuum system as, for example, PVD systems would have. And then some people say, oh, ALD is leading to less purities, lower purity than PVD. But that's, I think, for a large part because you don't use the same kind of vacuum system. So if you want to make a very high purity nitrides, you might have to work on your vacuum system. And what is so special about ALD is, of course, that you have a pretty long cycle times. And if you have a cycle time of like 20 seconds or whatever, then during this cycle, the surface, this atomic layer that you have deposited in one cycle, is exposed to the vacuum for a pretty long time. And this vacuum is not very pure. If there was some water in that vacuum, then of course that atomic layer is exposed to that water for a relatively long time. And I will show now a plot that I find very interesting, and it's not about ALD, but it's about PCVD of amorphous silicon. Pretty old paper, but what they found, and I think this is an interesting insight, what they found is that when they were depositing PCVD of amorphous silicon, they also had issues with oxygen contamination. But the faster they would deposit, this is 1/, the deposition rate, so the faster they would deposit, the impurities would go down. And you can explain this by the fact that if you grow faster, the oxygen in the vacuum system has less chance to get incorporated. Yeah, and that also was for an ALD system. Of course, you have a relatively slow deposition rate. You make an atomic layer every 20 seconds maybe, and that atomic layer is exposed to this vacuum for a relatively long time, and that's how your impurities can come in. And to prove this, we did actually a test. This was hafnium nitride that we were able to deposit in our system. And we typically would have a cycle time of 20 seconds, and then we would still have some oxygen, as you can see here in XPS. But then we artificially extended our cycle time. So we went from 20 to 40 seconds, and then to even to 100 seconds. And we saw that there was more oxygen in the film. The cycle for the rest remained the same, but we had this longer cycle time. And this makes sense, I think, because we could do a calculation. So this is the number of hafnium atoms that we deposit per square nanometer per cycle. And now we expose this number of hafnium atoms to oxygen from water, if we take that as the most important source. So we can calculate the water level or estimate, we can calculate the density, we can calculate the velocity of the water. We have a certain cycle time, and then we can calculate how much oxygen from water is reaching the surface. And you can see here that for 20 seconds, this, and that's an estimate, this level is as much as this one almost. And if you go to 100 seconds, well, then this would be 5 times higher than this, and then it would even bigger than this. So, of course, we have to make an assumption about the sticking probability here. So if you assume at 1, you can calculate the oxygen concentration. It might be lower than that. But what I would like to point out here is that the vacuum system is, of course, very important if you want to make low oxygen impurity nitrides, or maybe other materials that you don't want to be contaminated with oxygen. This is not an issue for oxides, but for nitrides and maybe other materials, this could be an issue. There is one interesting paper I find by KG Lasker. They were apparently also facing issues with their purity, and they were doing all kinds of studies, and it's a pretty nice paper where they were pointing out that gas purifiers help. They were pointing out that they also had an issue with their O-rings that they were using, and also there's a temperature dependence because the ALD chamber walls are relatively hot. So they also find that, and they came up with another solution. They could have gone to metal gaskets, I think, but they came up with a differentially pumped seal systems to really reduce the oxygen in their films. So I think that actually demonstrates that you can deposit high quality nitrides with ALD, but you have to think a little bit about the ALD system. Okay, so that was about equipment. Takeaway messages. There are 3 main classes of plasma ALD reactor configurations: direct plasma, remote plasma, radical enhanced. But given that there's a large variety of plasma ALD reactors, there are various plasma sources, subset types, operating conditions. So it will very much depend on your application. I pointed out that in high volume manufacturing, all the big companies that are typically using capacitively coupled plasmas. It works very well for 300 millimeter wafers. And sometimes they use then this spatial ALD system where they rotate the wafers to the different zones. On the other hand, for R&D, we see mostly remote plasmas, especially inductively coupled plasmas, but also other sources. And they give usually more flexibility, and also in process design, but also typically in ways to monitor film growth, for example, by analytical tools. All right, that was the second part. Let me have a look at the Q&A. We'll take a little bit of time also now to see whether some questions have come up. There's quite a lot of questions.
Erwin, I'll let you mark them as live and done as you go through them. I think it'll be a little bit easier since you're taking them.
Yeah, okay. Yeah. So there was this question, what's the base pressure in the hafnium nitride oxidation study? That was a system that had a turbopump, and that base pressure was around 10⁻⁶ torr. So that's actually already low pressure, but of course that is way higher still than what people typically use in PVD systems for such materials. Okay. Any tips for users who will fill their own ALD precursor bottles? Well, my tip would be, my tip would be that you only do this for chemicals that are easy to handle, which are not dangerous. So we typically do this with some precursors that are not really dangerous, or we do it in our own glove box system. Things like TMA or other precursors, I would not do this. There are many things that can go wrong. And also when you fill them yourselves, of course, you might also have the risk of introducing impurities. So it depends a little bit on how good you are with that, but be careful with that. But you can do it. It depends also a little bit on the application, how important impurities would be. Then there is a question about QCM and plasma-assisted ALD. That's a very nice question because QCMs are a little bit harder to use during plasma systems. QCMs are quite hard to use anyway, I would say, because they're very sensitive to pressure fluctuations and temperature fluctuations. So even in thermal ALD, it is a little bit tricky, and there are some good papers that describe what you need to do, but you might not be able to apply them during the actual conditions of your regular process. And when you use a plasma system, it becomes a little bit more complicated because also your plasma, when you strike the plasma, can have an effect on the QCM, so you might have some initial effect. It is possible, we have demonstrated it, we have a paper on this, so it is possible during the plasma step, but you have to be careful that you keep your pressure pretty constant. And of course, that also the pressure, the temperature is not varying too much, but it is doable, but it's not the easiest method, I would say. Okay. Film stress as a result of the plasma. I will show you some results later, but film stress, it can happen by ion bombardment, but you can also control it by ion bombardment. So it is something to take into account. It's in general, I think you have to take film stress into account, but I will show you also that you can control the film stress by for example, controlling the ion energy. So it is certainly a thing to be aware of because you can get delamination and this kind of things. That holds for thermal and plasma ALD. With plasma ALD, there are some knobs that you can maybe turn. Okay. Does ion bombardment of the grown fill surface affect the GPC of the process? Yes, it can. Depends a little bit on the, I will show later result where it does affect the GPC. So that's something to be aware of. Yeah, I will show you later. I think in the next part, I will show an example. Are there any ion beam assisted deposition systems? Well, not really, apart from those where you can do subset biasing, because you could see that a little bit as a where you add an ion beam and where you can control the ion energy. But I'm not aware of any other real ion beam assisted systems for ALD at least. Huh? Do high vacuum ALD precursor source differ mechanically from those medium or low vacuum system? Well, I'm not completely sure how to interpret this. Huh? So the ALD precursor, if you want to work with high purity, you certainly want to use that in a stainless bubbler, stainless steel container, and also your piping of and your valves between the bubbler, the container, and of course the reactor. You have to lay out properly with stainless steel piping to avoid, of course, leakage, where you will have some introduction of your, where if they are leaky, of course, then they would also introduce contamination. So I would recommend doing that properly always, but certainly if you want to work with under high vacuum conditions and with high purity, then also you have to think very well about how you design your your precursor delivery system. How do different power supplies affect film properties? That's a good question. It's not so easy to answer because in some cases there might be hardly an effect. So I think for aluminum oxide, I think the power supply doesn't really matter so much. In other cases, there might be some influence. For example, low frequency power supplies, they usually have more ion bombardment than radio frequency systems. And therefore your ion contribution will be higher, and that could affect your film properties, depending on the material that you're depositing. So, but that actually boils down to the question, what are the reactor species arriving at the substrate? And that's something I will talk about in the next part. So maybe you can say a few more words then. Okay. Is substrate biasing compatible with CCP as well as only ICP? Substrate biasing is very easy to do in remote plasma systems. So it doesn't have to be an ICP system. In CCP, it's a little bit harder, but you can actually work with ion bombardment by putting, for example, your substrate on the driven electrode. So that's one thing. So you can go to high energies by putting the substrate on the other electrode, or you can work at lower pressures. Having real independent control of your ion energy, as with remote systems, is a little bit harder. Okay. Well, there is quite a lot of questions, so let me see.
If you want to take a break and kind of review, maybe you can select the highlighted ones and come back with some answers for those. I know we can't answer all of them. Just so everybody knows, we've got about 19 more questions in the Q&A for Erwin.
Yes, yes. Maybe you can do one or two more. Just
Okay.
quickly.
Yep.
So direct plasma CCP, can that also be used for insulating substrates? Yes. Your substrate doesn't have to be conductive, also in ICP systems, because that's why you use radio frequency power supply. So it's not a direct current, but you use a radio frequency system, and that makes it possible to use insulating substrates. And the question about what are the typical energies you bombard the substrate surface? Well, I think that was already shown in the plots. I will come back to that later. Depends on the plasma configuration. It can be 20 to 30 eV, or when you increase it by biasing, etc. And I will later show some effects of that. So I'll come back to that later. And then to wrap up, the picture that I showed of the lab, that is indeed actually our lab. So you had a glimpse in our lab. And you're, of course, welcome to have a look once when you're over in Eindhoven. Let's have a break of 10 minutes right now, and then continue.
All right, we will come back at 12:15, and we'll see everybody at, 15 minutes past the hour, because I know many of you are in different time zones. Sorry about that. So we'll go ahead and take that break and come back shortly. Again, keep typing your questions. We'll field them as quickly as possible. But again, we have a lot of them, and I want to make sure Erwin has enough time to finish the presentation for everybody. And hopefully your questions will be answered as we go along. So we'll see everybody back here at 15 minutes past the hour. Thank you. One second. Sorry, Erwin. I realized I closed my slides. All righty, we are at 15 minutes past the hour. There's still questions in there. We're just going to do a couple of minutes, get through a couple of questions, but I think we should probably carry on with your presentation as well, hopefully answering those along the way. For some of you, I don't have your names in full in the list of participants. So if you don't have your name associated with that, can you please reply to my chat to you? Thank you. All right, Erwin, you're set.
Well, yes, let's do a few more questions. There was a question about, is there any motivation for using a mixed plasma gas, like argon and oxygen, for example? Well, yes, there is. Sometimes the plasma generation is a little bit easier. For example, when you mix argon to a molecular gas. One particular example is, for example, hydrogen plasmas. Sometimes they're a little bit difficult to strike. So then people use, for example, argon gas to that. I don't think that, well, roughly speaking, that the noble gas that you mix is going to have a lot of impact on the film properties. Although if you really use ion bombardment, then the ions could be somewhat heavier when you use, if you, for example, mix argon to an hydrogen plasma, because hydrogen would be probably the most dominant ion would be H3 plus, and in an argon hydrogen plasma would be argon H plus. So that could be an effect. But yeah, people do it quite commonly, and I think it works well. What are the advantages of using an ECR plasma? Well, that's a good question. There was at some point there was a commercial offering of ECR plasmas for plasma assisted ALD. I don't think they still do this because maybe the advantages weren't so clear. And an ECR plasma, the advantage of an ECR plasma is typically that you work with at very low pressures and relatively high ion densities. So it's real and high density plasma. But the drawback, I would say, is it's a little bit more complicated source. You need microwaves, and microwave power supplies are expensive. And then you also need to control the magnetic field. So yeah, I'm not so sure whether there's a real good reason to use ECR plasmas, but it might depend, of course, on your application. Another question is about the difference between self DC bias and DC bias for ion bombardment. Yeah, actually, well, I can talk about DC bias and self bias for a long time, but I don't think there is, if the question is about the role of ions during deposition, it doesn't matter so much how the DC bias is generated. It's just about the energy of the ions that is the ruling parameter, and whether that's the self bias or a bias that you generate by RF biasing, that doesn't really matter. And I will show you some effects later by some ion driven effects later. So hopefully that will clarify things. And then there is a question, I think the last question before we continue with the rest, is how much variation is there in ion lifespan from atom molecule to molecule? And can you provide a comparison list of different ion species lifespans? I don't think that's known. In principle, an ion would, at least I don't know it. I don't think it's generally known, because what people assume is that ions, when they reach the substrate, they recombine. So then that would be recombination at surfaces, at the reactor wall, for example. Of course, then you could have recombination in the gas phase, and that really depends on the kind of species that you're using. So it's not so easy to answer that in a general way, I would say, unfortunately. All right, I will continue now. There was some other questions. I hopefully will come back to them later, but let's also make sure that we can cover a little bit more of the topics that I would like to address. I would like to continue now about plasma surface interaction, which is of course very important because that's what we want. We want the plasma to interact with the surface. And there are quite a few interesting aspects that we need to discuss. The plasma surface interaction has consequences for conformality because radical species can recombine at surfaces. We already discussed ion surface interaction, so we'll come back to that later too. Plasmas they radiate, and they can also lead to radiation damage. So that's some aspect to consider. And then the plasma also interacts with the wall, and that can also have some effects. So I think this are some topics that I would like to discuss. This might be also a pretty extensive block, but I think understanding these things, or at least being aware of it, is actually very important. Okay. Okay, there we go. Well, in this schematic, we try to summarize some of the plasma surface interaction. Here we have the substrate. This is the reactor wall. No, I lost my, yeah. And in a plasma, we have all kinds of species. And these species interact with the substrate. They do that in a positive way. They contribute to the surface chemistry. But they can also lead to surface damage. Yeah? For example, ions or photons, they can lead to surface damage. Then some species might, like ions, they can be directional. Other species can actually be more random. And every time when a reactive species, an ion or a radical hits the wall, you can have kind of recombination reactions because they're reactive and they can also react at surfaces. I will come back to that in a few minutes. The other thing is that when we do plasma assisted ALD, we create reaction products. We burn off, for example, the surface groups. And these reaction products, they're not simply only pumped away, but they can also be excited again in the plasma. Yeah? And it holds for species that come from the surface of the substrate, but it also holds for species that come off the wall. And they can be excited again and be dissociated again, and then they can also redeposit. And that depends on the resonance time. So that's another effect that you have to be aware of. And I will discuss these things one by one in this section. I will start with the conformality. I explained that ALD is a surface-controlled method, and also PAALD. Not sure why it disappeared here. And that's different from flux-controlled. But there is, for plasma-enhanced ALD, there is something that you have to take into account. And the reason is that we work with, I showed this slide before, we work with radical species, oxygen atoms, for example, and they have the largest contribution to the surface chemistry. But these oxygen atoms, or other atoms, hydrogen atoms, nitrogen atoms, they can recombine at surfaces. And that's what we call surface recombination. An oxygen atom can hit a surface and meet another oxygen atom and leave the surface as O2. So then a radical picks up another radical and forms a stable molecule that is not reactive with the surface anymore, but also doesn't contribute to film growth. O2 is a pretty stable molecule. And now it's important to realize that if you want to grow a film in trenches, you might have several wall collisions before you reach the bottom of the trench, or almost the bottom of the trench. And every time when you collide with the wall, you can recombine. The species can recombine. So the remaining flux after one collision is 1 minus r. After 2 collisions, it's 1 minus r squared, etc. So the flux will really be decreased a lot when I have a lot of collisions. And this could have some adverse effects on the conformality. And that's something that we have investigated, and I will share you the results here today. And how we did these experiments was with 3D structures, but now not with vertical trenches that I showed earlier, but we use these special substrates shown here, which are called pillar hole chips, and these are lateral high aspect ratio structures. And they have been designed by VTT and Chipmatic sells them. And basically what this structure is, it's a lateral high aspect ratio structure. So that is basically a membrane that is supported by little pillars. And then in the middle here, there is a gap. There's a slit. And now, and you see that here, and now the species from the plasma and the ALD, they can diffuse into this cavity here and deposit the film. And now the advantage of this method is that you can quite easily analyze this film, especially here at the bottom, because you can remove the membrane by Scotch tape, and then you will see the film here being deposited to a certain distance. And you can measure this film thickness by imaging methods. So here the film has come to this distance, and you can measure the thickness as a function of position. And that's much easier, and you can do this much more carefully than in a vertical structure typically. And here I show some results. So this is thermal ALD of alumina from trimetallumina water. And we see here now the top of this bottom here. We took off the membrane and we looked at the film thickness. These were two particular conditions that we used. And one, we were limited by the TMA dose, and the other one, we were limited by the water dose. So we see that we have a high conformality. This is the aspect ratio, basically. But here we just dosed too little TMA to get as deep. Here we were limited by the water, because this cavity is so deep that you would have to extend your dose time a lot to really reach here the site. So that's why you also the conformality is not perfect here, because you dose only for a certain moment. Now, by looking at these profiles, we can determine, and I'm not going to elaborate too much about that, but you can read this in the literature. You can determine also the sticking probability of these species. So if we are TMA limited, we can determine the sticking probability of TMA, and we can determine the sticking probability of water. And that's, of course, very helpful for understanding and for example, for modeling purposes. And I will show you now a few slides to give you a little bit of feeling of what you need to take into account when looking at conformality. And this holds for thermal ALD and also for plasma ALD. So one thing that you have to realize is that you can have two growth regimes. You can be reaction limited, or you can be diffusion limited. And here I show the reaction limited case. So here in blue, it's the precursor density, and then in red is the deposition. And if I'm reaction limited, then means that the sticking probability is very small, or actually this product is very small. And then if that means that the species will diffuse inside the trench and then only react. The reaction takes long time before longer time than the diffusion. So basically, you first will get kind of a constant density inside the trench, and then I will see the film growing. That's basically how you can see this. That's what we call the reaction limited conditions. The reaction at the surface is limiting. It's not the transport that is limiting. And for those people that are interested in this, if you have this kind of conditions, you don't have to extend your dosing time when you go from just planar substrates to 3D substrates. You basically can use the same dosing time because you are reaction limited, not transport limited. Another example or another case, which is very important, and certainly for these high aspect ratio structures that we have, is what we call diffusion limited growth. Now, this product is way higher, and you can, for example, have a high sticking probability, and then you're diffusion limited or transport limited. So your species will diffuse in, and immediately when you're diffused in, they will react, because the reaction is very fast, but the diffusion is basically limiting. So then the film profile, the species will diffuse inside the trench. They get deeper and deeper because here you reach saturation. And then the film will keep on growing and you will diffuse inside the trench. So that's what we call diffusion limited. If you're diffusion limited, then it's important that you really extend your dose time when you start using these structures. If you would use, if you deposit on a planar substrate, then the diffusion is not the diffusion time is not that long. But if you're now going to use these 3D structures or other 3D structures, that doesn't matter. But if you use 3D structures, you have to extend your dosing time quite a bit because, yeah, diffusion is limited. And you have to give it more time for the species to diffuse in these 3D structures. This holds for thermal ALD and holds for plasma ALD. And the sticking probability that I showed earlier for thermal ALD can now be determined from this, this growth front. If the sticking probability is small, then you have a much more shallow growth front than a high sticking probability. And I have another animation, I think. So you see this, and then you can calculate the sticking probability from this slope. And then you can use this equation and to look it up for this slope, and then you can determine the sticking probability. It's all in the paper that I've referenced. Now, well, and that actually was what we did here. Just to come back to that. Now, when you use plasmas, then you have a third case, and that is the case of recombination limited growth. If the radicals that you use can recombine at surfaces, even when the surface has been saturated, then you have to take that into account. Oxygen atoms, they can recombine here on the alumina surface and on the silica surface, for example. So they can recombine on all surfaces, whether it's saturated, yes, whether the ALD growth is saturated, yes or no, they can just recombine. And then if you have a high recombination probability, the species will not go that deep. And here you see what happens for the different recombination probabilities. If the recombination probability is pretty low, you can have quite some diffusion inside the trench, but if the recombination probability is very high, you don't get deep. And you can have some equations for that. And you see here basically what happens. And then you have to increase your saturation time or your dosing time also given by this equation. So that's somewhat similar with the diffusion limited case. Okay. So we did this kind of test with these structures for different plasmas. And well, let me first show here now the case of silicon oxide. So this was plasma-assisted ALD of silicon oxide, where we varied the plasma exposure time, and we see that we go deeper inside this lateral aspect ratio structure when we increase the dosing time. And this can be due to the diffusion of the oxygen atoms, but also due to the fact that your recombination is playing less important role when you extend the plasma time, because then it's more likely that you have species arriving here. Okay, now the good thing here, independent of the interpretation, is that we can see that for plasma-assisted ALD, we can get pretty deep. This is an aspect ratio of 800. And that means that we can conformally code aspect ratios of 800 by plasma-assisted ALD. So that's very good news. So we can code high aspect ratio structures very conformally by plasma-assisted ALD, at least for the case of silicon oxide. And from the analysis of the data, we could calculate a relatively low recombination probability. So that explains that we can go so deep. So that's important. This is important data for modeling studies, for example. Now we applied this method for different materials. I showed already the silicon oxide case. We also did titanium oxide. Also for titanium oxide, we can go very deep. Aluminum oxide and hafnium oxide, you see it's slightly different. We don't get that deep, even if we have a long plasma exposure time. So it's more difficult to get conformal film growth for these two conditions compared to these two. Now, these aspect ratios that we reached here, 40 and 80, are still very high aspect ratios. For many applications, you don't need this, but there is a difference. So this might be still okay for many applications, but there is certainly a difference between titania and silicon oxide. And the difference is in the fact that the recombination probabilities are different. They're way lower for silica and for titania than for alumina and hafnia. So that's interesting. That's important to know. And as a matter of fact, these recombination probabilities also depend on the substrate temperature. As you can see here, the drop with substrate temperature. For the other materials, they are way higher, as I showed earlier. They even depend, and you only have data for silicon oxide, they even depend on the plasma pressure. So you see that, whether the conformality will depend somewhat on the operating conditions. That's interesting information. Come back to these structures that I showed earlier. This is a relatively small aspect ratio. It's not that high. And for these cases, we can see that we can still grow conformally. Even the aluminum oxide is still very nicely conformal. So I showed you earlier that the limiting case, but for many applications, plasma-assisted ALD is just very conformal. But if you really try to stretch it, then you might see the effect of the surface recombination. And as a matter of fact, here I show even narrower trenches. This one is wider than this one. And you see it's still very conformal. And as a matter of fact, what we see here is the so-called gap fill method to fill up a trench by materials without any hole here. And this is one of the big applications of ALD and certainly of plasma-assisted ALD in the semiconductor industry. We'll come back to that later. Just to zoom out a little bit, I showed you the recombination of plasma species, but this is not only something that happens for plasmas, but it happens for all very reactive reactants. Also, ozone is pretty reactive at surfaces, and you see similar effects there. So don't think that you can avoid this by going from an oxygen plasma to ozone. You have the similar things there. Maybe it works slightly different. Maybe it works different under different conditions, but also ozone can recombine at surfaces. Also, that can fall apart at surfaces. Yeah, that's why you can't buy an ozone in a gas cylinder. You have to make it on site. And in an earlier study, a long time ago, we actually showed that this even affects the uniformity of materials because ozone recombines very easily on zinc oxide, for example. So it's more general than just for plasmas. Okay, so that was about the conformality. Some important information, I think, and hopefully that answers several of the questions. Then next, I will come back at the ions. We talked about it a bit, quite a bit. So these are some typical ion parameters: ion density, ion flux, electron temperature. So that's more about the electrons, ion energy. And I showed also this plot. This is for a grounded substrate. We would have like ion energy is less than 30 eV in this particular case. And we also know the flux. So I showed this earlier. As a matter of fact, we can plot this in the this data. We can plot in this plot by Takagai. He made a plot of the ion flux density and ion energy for different plasma processes, implantation, etching, deposition. And this is basically where we are with our ALD conditions. And he also plotted some of the mechanisms at the substrate. And what we see is that in our ALD conditions, the energy is too low for implantation. The ion energy is typically too low for sputtering effects, but it might be high enough for desorption, ion-assisted desorption or adatom migration, that the ion energy might be high enough for that. And these kind of things can maybe affect or improve the film properties. And what you also can do is that you compare how many atoms per cycle that you deposit you can compare this with the ion flux and basically with the ion energy per deposited atom. So that's a calculation that we did. So this is how many atoms we deposit per cycle. And on every cycle, we have the material exposed to ions, and then we can calculate the ion energy per atom deposited. We see that we can have very low values for aluminum oxide, but here for titania, apparently we have quite some ion energy that is delivered per atom deposited. And of course, this ion energy can have an effect on the film properties and well, improve it or maybe deteriorate it, but you cannot just neglect this effect. Well, this is the typical conditions that I showed earlier. Now, if you don't want the ions to have any effect, then I would suggest to go to high pressures, because I explained earlier in the plasma sheet, at high pressures you will have collisions and then ions will lose their energy. If you do want to have the ions, then you can go to subset biasing, or you can, for example, use the CCP plasma configuration and try to optimize the ion energy in that case. And then you can play around with this. I will show both cases. So this is an ICP plasma where we have looked at the ion energy as a function of the plasma power. We see that we don't have too much effect, but the plasma pressure does have a big effect. So if you work at high pressures, the ion flux and also the ion energy really drops a lot. And this is mainly due to the collisions in the plasma sheet. So working at high pressures, then you lose the influence of the ions. If you want to increase the ion energy, and I mentioned this already earlier, then we can go to RF subset biasing, and we can go to these high ion energies. And these are measured by subset biasing. We use this RF bias that was also leading to this saddle shaped figure. And we use this RF biasing because we use insulating substrates. There was a question about that earlier too. And one of the interesting things that we found in our research was that this ion energy can be really nice for some applications. So here we see tinitride and hafnium nitride. And what we see is that the material properties very much improve when we have some ion energy. So this is the bias voltage, which is kind of a measure for the ion energy. So we see that the material properties really improve when we have more ions, more energetic ions. And here it even drops an order of magnitude. So this is really one of the beneficial effects of the ions. We can make much better quality material, much more conductive nitrides than without biasing. Okay, so that is one part about the ions, the control of the energy and some impact. What I would like to do now is look also at low energy ions. And again, we're going to use this special structure. And this is a pretty interesting study that we did. So now we're going to look at low energy ions, 30 eV. And here you see some ion energies measured, all less than 30 eV. And we're using these structures right now, and the ions will not be able to penetrate this structure. So the radicals will lead to deposition, but the ions will not. Here in this opening, we will have the ions. And now we can look at the quality and the film properties for this region and that region. And there we saw some interesting effects. I will go over this step by step. So here we look at the growth per cycle or the thickness inside the cavity. And there we have for 12 seconds or 120 seconds, we have the same thickness. In this opening, we see that the film is less thick for 12 seconds than inside the trench. And even smaller, the thickness or the growth per cycle for 120 seconds. So apparently the thickness decreases with ion exposure. No ions, Little exposure here, more exposure here. And then this is the quality of the material. This is the wet edge rate. That's a typical quality test. The wet edge rate is at a certain level inside the cavity. The wet edge rate drops when we have some ion influence, 12 seconds of ions per cycle. And here we have even more ions, and then the wet edge rate almost drops to 0. Not completely, but very low. So what we learn here is that the material quality improves with ion exposure, even for 30 EV ions. And this is basically another representation of the data. Without ions, we don't see any influence of the plasma exposure time. With the ions, as long as we are saturation, with the ions, we see a dependence of the growth per cycle. And we also see an improvement of the material quality. And the material quality here really approaches the one of silicon oxide, thermal silicon oxide. So we attribute this effect to the fact that we enhance some of the surface reactions by the ions. So it's not sputtering or something. We think that we remove some of the hydroxyls and that we have some effect by the ions. And that also leads to denser, more packed films. We looked at various conditions. So here we did a lot of experiments, varying all kind of parameters. And we see kind of a scattering here. And then we introduced the following parameter. The ion energy dose is the plasma exposure time, shown here, times the ion flux that we were able to measure, times the mean ion energy that we also were able to measure. And if we now plot all this data as a function of the ion energy dose, as we did here, we see that everything lines up at this nice trend, and that the ion energy dose is apparently very important for what's happening at the surface. So that was a pretty fascinating effect. And that shows that even low energy ions can have an effect. Then we went to titanium oxide. So we did the same thing. Now it's titania here. And also here we saw some interesting things. So silica was thinner here and thicker here, less dark here in the ion exposed region. Titania was the other way around, darker in the ion exposed region. And when looking at the growth per cycle, we saw that the growth per cycle is higher where the ions hit the surface than where they don't hit the surface. And when we and that actually, and for silicon oxide, it's the other way around. Coming back to this figure, we actually also see the effect here, because if we look carefully now at the planar surfaces, we see that the silicon oxide is always slightly thicker at the planar surfaces than at the sidewalls. And for titania, it's the other way around. Titania is slightly thicker at the planar surfaces than at the sidewalls, and here the sidewalls are thicker than the planar surface. So we see this effect back. And for titania, we also saw, if you look at the wet edge rate, that the wet edge rate would be a certain value inside the trench and would be very low in the ion exposed region. And we did some Raman spectroscopy, which we could map, and there we found that the film in this ion exposed region is a little bit crystalline, while the film in the trench, which not exposes to the ions, is fully amorphous. So that explains the wet edge rate. So the bottom line here is that the ions, even if they have low energy, they can still have an effect on the film growth and also on the material properties. And as a matter of fact, it can also have a positive effect, right? Okay. Then two more topics. One is the radiation and the possible damage. So I showed plasmas, they emit light in the visible. We can see this. We can look through a glass, and then we see the emission. I also mentioned that we have maybe photons with high energy. And we see for oxygen plasma, we see these photons with an energy of 130 nanometers, which is more than 9 eV. This 9 eV is higher than the band gap of aluminum oxide and silicon oxide, so they get absorbed in these materials. And they can cause damage. They can lead to ionization or depassivation. And this is well known from some other plasma studies. Yeah, so very high energy photons, they can lead to damage. Doesn't have to be bad in the end, because often you can anneal it out or you can work around it, but it is something to be aware of. And we actually have proven that this happens. What we did is used a solar cell test sample. I will not go into detail, but this is a test sample where we could really look at the quality of the surface, and we could measure the effective lifetime of electrons and holes inside the silicon. And an effective lifetime which is high is good. And what we saw, if we expose this surface to plasma, I don't know, different conditions, and for different plasma exposure times, we saw that the lifetime would go down, and therefore the surface properties would deteriorate. And this was depending on the plasma conditions. More intense plasma, more intense plasma would go faster than a low intensity plasma, and we see that goes down as a function of time. So this really proved that it's surface defect generation. The fact that these are photons, VUV photons, we were able to establish by using filters. So we added a filter on top of this test sample, and we used two types of filters, a quartz filter and a magnesium difluoride filter. Both would shield the surface from ions, obviously. The quartz filter would block the UV, the VUV. The magnesium fluoride would transmit the VUV. And then we would look at the change as a function of plasma exposure time. In blue are the normal conditions without any filter. In magenta, we see with magnesium fluoride, we still see the same decrease in effective lifetime. If we block it with quartz, we see nothing is happening. So this really proves that VUV photons can lead to surface defects. And that's something to take into account. And often people are, if they talk about plasma damage, they're very afraid of ion damage. I think VUV photons might be more detrimental, and you have to pay attention to those maybe more than ions. There are ways to work around it using a higher pressure, for example, because you have a lot of self-absorption of the photons, so that might work. But it is certainly something to be aware of. And of course, the particular case for the silicon, for the solar cell test sample, we could anneal out these defects by doing an anneal at 400 degrees C, so that was another solution. Okay, the last thing here that I would like to talk about is now plasma wall interaction. So the plasma will remove species from the wall, from the substrate, the ligands from the substrate, but also from the wall. And they can come into the plasma and then lead to effects that can affect the plasma and that can affect the substrate. It doesn't have to, but it can. And I will show now some results for plasma-assisted ALD of aluminum oxide. I showed this earlier. When you do a plasma, oxygen plasma, you burn off these ligands. You make CO2, CO, and H2O, and regenerate your OH. And with mass spectrometry, we were able to see these species being generated. Okay. Then we just had a look at a plasma, and we made a movie, and I think we can demonstrate a very interesting effect. So this is an older movie, but we look at the plasma, and we look now at the plasma strike under two conditions. One is a pure oxygen plasma, and the other one is an oxygen plasma after precursor dosing. And I will show it once more. The regular plasma strike, the plasma becomes green right away. But here it turns blue first, and then it becomes green. So when the surface is basically having the aluminum oxide or the trimetalaluminum species at the walls, show it once more, then the plasma is really affected by that. And here it's visible because it's extremely clear. So what's happening here? Okay. What's happening is that at the wall, we produce CO2, water, etc. And these species will come back into the plasma. They come from the wall, they come into the plasma. The plasma has hot electrons. These hot electrons can collide with the species and make and dissociate these species, but also excite them. And if they excite it, they can emit the radiation. That's why where the plasma emits radiation. Now, for pure argon plasma, for pure oxygen plasma, I have some emission lines by oxygen. But once I have done an ALD cycle or half an ALD cycle by exposing the surface to trimetalaluminum, I have CH3 groups at the wall, and then these species will be created when I strike the plasma. And this is the spectrum, the blue spectrum is taken right after the plasma strike. And then I see a lot of additional emission, which turns the plasma blue. And as a matter of fact, most of the emission is coming from excited CO. So actually from this species. What this demonstrates is that the plasma is really affected by the wall conditions. And here we could see it visually. The plasma, when you strike the plasma, first the plasma is affected, and maybe the matching of the power supply is affected, etc. So that's something to take into account. Another case is silicon nitride. Here we would have a similar effect, but we could not see it by the naked eye. Silicon nitride, you have the same effect, but we saw some other effects. The case of aluminum oxide, we did not see a negative effect on the film properties. But for silicon nitride, we saw an effect that we would like to avoid. So what happens is that the plasma leads to feedstock species that react at the wall or at the substrate. This leads to reaction products. These reaction products get excited, and then they can redeposit. And whether they can redeposit depends on the material. For silicon nitride, that can happen. And it depends on the residence time. And the residence time is basically how quickly we purge out the gas. So the residence time is decreased when we have a high pumping capacity. Here you see the effect that we couldn't measure with optical emission spectroscopy, so it was not visible by eye. So this is basically how we switch on the plasma. Here you see the emission of N2. And here you see some transient species, and this is due to the reaction products. This is excited CN, and that comes from the wall species. So the released reaction products are cracked in the plasma, so they can, and the reactor species can redeposit unless flushed out of the reactor quickly. And we saw this correlation now between the film properties, impurity content, and wet edge rate with the plasma gas residence time. If the residence time is very high, we saw that we have more impurities and a higher wet edge rate. If we decrease the residence time, so have faster pumping, we would hardly see that effect. So I think this is showing how important this plasma surface interaction is. And that's the other effect that I would like to mention, plasma wall interaction. Okay, end of part 3, takeaway messages. So plasma-assisted ALD can conformally cover high aspect ratio structures. No problem in most cases, but it does depend on the material and process. Some cases are extremely easy and nice. Some other ones might be a little bit harder. Second thing, ions can play a significant role even for fairly low ion energies. Yeah? And it can be a positive or detrimental role, but we saw some very nice effects and positive effects from the low energy ions for example, for silicon oxide. Plasma damage, always have to be aware of that, but I think you have to be maybe more afraid of photons than of ions, I would say. And then I explained just a minute ago that plasma wall interaction can affect the process and materials. And for example, you might have to optimize the residence time for the plasma gas. Okay, so let's go to the Q&A. Again, quite a few questions. Yeah, there was one question about how the ions are accelerated in the plasma sheet and whether you can control this. I think that should be clear right now. So by controlling the you can increase, for example, ion energies by substrate biasing, RF substrate biasing, for example. Then you can increase the ion energy, and that's done, for example, for etching, and you can also do this for plasma enhanced ALD, as I showed. Decreasing the ion energy can usually be done by going to higher pressures or by making the reactor more symmetric, etc. So hopefully this is clear right now. And then, yeah, that's a similar question. What controllable parameters in PALD system can be used to modulate and control the characteristics of the plasma sheet? It's mostly the, for example, external biasing. So then you control the ion energy. And of course, the pressure is an important aspect. I think that's also should also be hopefully pretty clear right now. Do different reactor species have different recombination rates, or recombination rates the same for all reactor species? That's also what I hopefully have addressed. So different reactor species have different recombination rates, and they even might depend on aspects such as the temperature of the surface or the pressure in the plasma. So they really vary. How can you determine if a process is diffusion limited or reaction limited? Well, you can make some estimations, I think. If you have extremely long, deep trenches, then you basically always diffusion limited. Whether you're reaction limited, for then you need some information about your sticking probability, or yeah, basically you need information on your sticking probability, or you need some estimation of that. So with some of the data that is available in the literature, you can make a guess. One other way of looking at it would be to deposit films, and if you go to higher aspect ratio structures and you are reaction limited, the conformality should not matter, because for the reaction limited case, you're not transport limited, but you are time limited, basically reaction limited. And the exposure time, you don't have to vary. If you're diffusion limited, then if you go to 3D structures with a larger volume, with a larger surface area, then you really have to increase the dosing. Hopefully that's clear. I can maybe come back to that separately. Can recombination also have correlation with radical concentration? Yes, if you have more recombination, also your radical density will go down, because a density in the plasma is basically a balance between production and loss. And if your recombination is higher, then you have more loss terms, and then your density will typically drop. Is recombination happening only at the substrate surface, or also during or inside the plasma during radical formation? I would say it's mostly happening at surfaces, radical recombination, not so much in the gas phase, because for gas phase recombination, you need collisions. And for example, oxygen collisions of oxygen atoms with oxygen atoms, you need a third particle. So typically these gas phase collisions are not very likely. That has to do with the collision dynamics, the momentum and energy conservation. So typically you can neglect gas phase recombination and you have only surface recombination. It's different when you go to high pressures, like you go 1 to 1 atmosphere, then this might be different. How is the ion energy measured? Well, that's a good question. I showed several ion energy distribution functions, and they are measured with what we call a retarding field energy analyzer. It's a small device that you can put on your substrate holder, and you can buy this commercially. And then you apply some voltages to grids, and then you can shield the ions. I don't have a drawing. It's a little bit difficult to explain it differently, but you can, if you look up retarding energy field analyzer, then you will find information on this, and you can just buy these systems commercially. Why do ions improve the properties of the tinitride film? Yeah, that was an interesting effect. Depending on the time, I might be able to come back to this in the next section, but the most important aspect there was oxygen. So the ions remove the oxygen from the surface, and that leads to the improvement of the tinitride. And we have done a very interesting study, not for tinitride, but for hafnium nitride, where we clearly saw that effect. I'm not sure I have time for it, but otherwise, I hope that I can come back to this. It's in the slides anyway. Yeah, can you speak to the impact of dangling bonds and the relationship to ion energy and film quality? So dangling bonds, if you're making a device on silicon and you make dangling bonds on your silicon surface, then that electronic quality of that silicon surface is deteriorated. That doesn't matter, for example, for MEMS application, but if you would like to apply a film for making a, for example, transistor, that would certainly affect the film quality and therefore the device operation. So depending on the application, dangling bonds might really affect your film quality negatively and the device performance. As I said, there are ways of mitigating it. A simple anneal was helping us, was actually removing all that effect, but it is something to be aware of. Yeah, dangling bond formation and ion energy, that's a little bit hard to say. Typically, you would say higher ion energies, more dangling bonds, but it's maybe not that easy because ions will just penetrate deeper in the material. So I think, more energies, more ions and more and higher energies are typically would lead to more dangling bonds, very roughly speaking. Can you comment on the stoichiometry of the films as a function of ion energy bombardments? Yeah, we looked into this. Maybe it's not so easy to give a general answer here, but I think in some of the cases, the stoichiometry even improved because we would remove some impurities, but maybe not for all conditions. In these slides that you mentioned, or that was discussed, you find some papers where you find some data on stoichiometry back. I suggest looking up those or asking those papers to me, and then you can learn about it. It might have a different effect for different materials, or does have a different effect for different materials. Can you give the best conditions to hydroxylate a surface with OH surface species? Is that a water plasma? I think that might be the best. That might be a very good candidate. I think with water, you will make a lot of OH species in the plasma, and that will hydroxylate the surface. There might be other possibilities too. An oxygen plasma might also be helpful because you usually also always have some hydrogen around. But the water plasma, I think, would be one of the best choices. Okay, maybe just a few more. What is the dimension limit of plasma ALD for coating high aspect ratio structures? So that is a very good question. As I said, that depends on the material. For silicon oxide, you can do, and titanium oxide, you can do very high aspect ratio structures. I showed aspect ratios over 800. For hafnium oxide, for our process that we studied, it was around 40. So yeah, for these oxides, I can give numbers. Typically, for most of the applications, I would say you're safe. But if you really stretch it, if you really push it, then you might run into issues. Having information on this, on the recombination probability is helpful, but of course you can also just give it a try and then look at the then have a careful look at those effects that are described, such as diffusion limited, reaction limited, and recombination limited cases. Okay. Are there any means to avoid high energy oxygen radiation? Yeah, I mean, for example, how you generate the plasma will affect that. So there are the different plasma sources might have a different effect. Of course, also whether there is line of sight radiation. So that's another thing where you can, which you can maybe control. If you reduce line of sight, then the radiation is not so important. Also working at higher oxygen pressures will helpful, because the VUV will be absorbed by the gas phase species themselves. They call that self-absorption. So there is certainly ways, and I think there was some literature of plasma etching also, how they, with plasma etching you would have the same issue. So, and there also they are able to avoid it to some extent at least.
Erwin, you want to go ahead and take a break here? I don't know how much time you need for your last section, so I'll let you advise.
Yeah, that's I will be able to cut a little bit. That is some optional parts. Maybe you can do one more question and have a break.
Okay. Yep.
But we're also running quite late now. Can plasma wall interaction be reduced by purge gas and by pump speed base pressure? Well, the species that you create, the generation of species at the wall, that can be controlled somewhat by, for example, changing the wall temperature, or changing also depending on the material, because some materials might not deposit at the wall but only at the substrate. For example, when the substrate is heated and the wall is not that heated so much. The generation of these species from the wall you cannot really avoid by purging or by pumping, but you can avoid the contribution to the process by, for example, changing the residence time. So then you just pump out these species faster. So, well, yeah, so in principle, what you say is true. So plasma wall interaction, the effect of plasma wall interaction can be reduced by having a higher pump speed, or by flushing the gas faster. Okay, so I answered quite a few questions. There are a few more to go, but let's see whether we can do them later. I think now it's time for a break for you and also for me, and then we will continue, I think, in 10 minutes.
All right, let's come back at 20 minutes past the hour. It'll be a little bit shorter of a break, but hopefully enough time to get up and move around and come back for our last section. Again, if you have questions, type them in the Q&A. I am waiting on a couple participants to reply in the chat who they are. Someone typed in some foreign characters that I cannot translate, and I believe someone is called in. So if that person can let me know who they are, that would be great. And we'll come back at 20 minutes past the hour. Thank you very much. All righty, we are at 20 minutes past the hour. I'm going to bring everybody back. And just a reminder, we're going to do this last section, answer as many questions as possible, but because everybody's in a different time zone, I know it's late for some of you, including you, Erwin. So we'll try to end as close to on time as possible. I'm going to drop an evaluation link in the chat. So remember to check that if you don't see it in your browser, and I will also send it via email. I'll do some closing slides after Erwin's last section and do any last questions we can get through. Okay.
Okay, thank you, Heather. We'll continue with the last part. And some of the slides that I had in there are kind of optional, so I will probably not be able to cover all the slides, but I think it's more important that we address your questions. And of course, we have addressed already many of your questions, and I will try to keep some time also in the end to do that. So, and the things that I will not discuss, you can look back at the slides and also look up the papers. All right, so in the last part, we will continue about applications and processes. And I think the most important thing to do here is talk about the applications. We'll talk about semiconductor applications, but also some other applications. And then maybe the other stuff I will be very brief about, or pick some things that I think are important, given the questions that you already had. All right, it always gives a little bit of issues the first time. Well, my slide doesn't want to continue. Oh, there we go. Yeah, well, we were talking about plasma-assisted ALD. And the first thing that I would like to point out is that obviously, and I will show this later, there are many applications of plasma-assisted ALD, but you really only use it when it gives some advantages over thermal ALD. Because when you use a plasma, you have to have a plasma source, etc. So you really only apply plasma-assisted ALD when there are some clear advantages. And as a matter of fact, that holds for ALD in general. You only use ALD when other thin film methods are not working as well. So also ALD you only use when the method is giving you some advantages over other methods, because ALD is a rather slow technique, etc., etc. So it holds it more in general, and it also holds for plasma-assisted ALD. But certainly there are many cases where it is very helpful, and I will show that. I will start with this slide about the general applications of ALD, also thermal ALD. So ALD is used a lot in what I call micro and nanoelectronics, seen here, especially in the advanced nanoelectronics, of course, but also in many other applications, power electronics. Then here in the reddish color, we see energy applications, which are typically larger area applications. Also this place has a large area application. So there is quite some use of ALD or in these applications. And then this is more, yeah, the other category, smaller applications, niche applications. There was a lot of use of ALD there too, but we often even don't know that people are applying ALD because the companies usually don't have any reason for sharing that information with you. ALD has certainly an increasing role in the semiconductor industry, and this is again for all ALD and PALD. And this is actually a plot for logic, but I really like it. This shows several technology nodes from the three big players in logic. And you see every time when they make a step in node, you see that the number of ALD processes is increasing tremendously sometimes. So there is a lot of ALD when you make the devices. And this is even not the latest technology nodes, of course. One important thing to realize is that not all the ALD layers will end up in the device. So if you open up a device, you might not see all the ALD layers that have been used to fabricate that device. And I think there are estimations, I know there are estimations that people are saying about only 50% of the ALD layers that you use to make a device end up in the device. So there are many sacrificial layers. And many of the plasma-assisted ALD films are sacrificial. That depends on the material quality, the material systems that you can typically make. So first I would like to focus on logic. Logic, you distinguish front end of line, back end of line. This is all ALD applications. But some of these, they are done by plasma-enhanced ALD. Source doping, gate spacers, gap fill, that is often done by plasma-enhanced ALD. Maybe not so much the gate oxides because of damage, for example, but these applications are using plasma. If you think about back end of line, that depends a little bit on the also in the material, but also here there are some plasma-enhanced ALD applications, and certainly in patterning either for back end of line or front end of line, there is a lot of plasma-enhanced ALD, and I will show this. First of all, this is a TEM image showing some FinFETs. So here you see FinFETs. Actually, here you see the FinFETs very clearly. And there you see some plasma-enhanced ALD applications, for example, for the solid state doping. Also for many cases for gap fill. You see a lot of gap fill applications. And for these gap fill applications, they often use silicon-based dielectrics, especially silicon oxide, for example. And that is a material that is very difficult to make by thermal ALD. And silicon nitride is even worse. So then you really want to use, I think, use plasma-assisted ALD, and that's what people are doing. So these are some of the applications. And the gap fill, I would like to remind you about this. All plasma-assisted ALD, we can fill up this gap pretty nicely. And also with plasma-assisted ALD, we can go faster than with thermal ALD. So that is one of the reasons that you might want to use this method here. Another very, very important application is of plasma-enhanced ALD, but also a very important application of ALD is in patterning, especially in self-aligned multiple patterning. And as a matter of fact, I think this is the biggest ALD market overall. So this is the biggest ALD market, and this is, I think, mostly plasma-enhanced ALD. Maybe some of the people here that are working at certain fabs, they know better, but I think this is a very big application of ALD and certainly of plasma-enhanced ALD. And it's used to basically make these FinFET structures, for example. So this is the 10 nanometer mode of TSMC, so it's a few years back. So you have these fins, and to pattern these fins, you need a special method because lithography is not good enough for this pitch. And certainly at that stage, EUV was not available yet. And then people had to come up with a trick. And I will explain the trick in a minute. By the way, nowadays we do have EUV lithography, but still this patterning is not done by EUV. It's too costly, and you can do this nicely by a combination of immersion lithography and ALD, plasma-assisted ALD. How does the method work? Before I come back to this slide, I will just explain the method and explain it for self-aligned double patterning. What you do is you apply your photoresist and pattern it the best that you can. So this is, for example, with immersion lithography, you do the best in terms of line width and pitch. And then this is after you have patterned the photoresist, you have these photoresist structures. Next, you apply an ALD film on top of the photoresist. And you need to work at low temperature, otherwise the photoresist will be affected. And you need to take a material that is very conformal. And silicon oxide is beautiful for that. Subsequently, you do an etch, an anisotropic etch, and you remove the material at the planar surfaces. Yeah, but the material here at the side will stay because you don't etch long enough. Then you remove the material, the photoresist in between. They call it a mandrel, so they remove it. And then you have these structures, and you can transfer them in the underlying material. And then if you remove this, you have now structures generated that have the double pitch from what you have started. That's why they call it pitch splitting. And the line width is now the thickness of the ALD film here. And that is what they call self-aligned double patterning. This was introduced for creating features such as FinFETs since the 20 nanometer node. So then they needed this method. And it's self-aligned, so that's the important aspect. So you don't have to worry about all kind of lithography trouble. And it's also used for other applications, but it's certainly used for FinFET formation. Now this is pitch splitting, but you can also do this trick twice. So you do this once, and then this is the silicon oxide, for example. But before you transfer this process into the material underneath, in the gray material, you first apply another film of another material, and yet you do the same trick. You etch away again, and then you can transfer that into the underlying material. So this is what they call self-aligned quadruple patterning. And now you have the pitch distance is now divided by 4 that you started with. And this self-aligned quadruple patterning was used to create these FinFETs. And people are still using this. In principle, you can do it as a third time octuple patterning. People have been looking at this. I'm not sure whether that's used in industry, but you can do this trick several times. And what's important is that you have a low temperature ALD process, preferably close to room temperature. And what I pointed out earlier, and also this slide, plasma-assisted ALD of titania and silica is very, very nice for doing this. And I think these two materials are used a lot. Remember the TEL tool that I showed earlier that had Tickle on there? So that's where they used the titanium oxide, and I think that's mostly for patterning applications, because you want to have a relatively high throughput, and that's why they use the spatial ALD system for these kind of applications. That's one example. There is more that you can do. I don't really have microscopy images, but this is just a cartoon to show what you else can do. Suppose that you want to make a contact hole of a certain dimensions, but this is too small to make with the lithography directly. Then you can do the same thing. You apply an ALD shrink spacer. You apply it everywhere, but you etch it away from the planar surface, and then it stays into the structure, in the contact hole. And then you can transfer that etch, and then you can basically etch that hole into the yellow material here. So that's how you can make a smaller contact hole. And then if you need, you can even do inversion spacer. So now you apply another ALD step, you fill up that hole, and now you etch away you make sure that you have etch selectivity, you etch away the other material, and now you can make that into a pillar. And then you have defined a small pillar by using a wide contact hole in the beginning. So this is another application. This is used, or has been used, and I think it still is used. In some cases now, this has been taken over by extreme UV lithography. But soon enough, extreme UV lithography needs to be combined with these kind of tricks again, because then the dimensions will be too small to do this directly with EUV. So this is an important application, and this is, in many cases, this is done, I think, with plasma-enhanced ALD. Another application of plasma-assisted ALD is silicon nitride for gate spacers. Here, I'm not completely sure what is now the state of the art in production. A couple of years ago, there was a lot of interest from all the companies in plasma-assisted ALD of silicon nitride. But that and there was a lot of research, and then this interest faded away. At least the companies did not collaborate on this anymore. which can indicate that the problem has been solved or that, you know, it was too early and that they postpone it. But this is, for example, the gate spacers. This is a planar FET FET, where you want to put the gate spacers here. This is for the replacement gate. And this is for a FinFET, where you use the gate spacers. And silicon nitride is a material that you can composite by PECVD. And that's, in the old days, this was used a lot by PECVD. But nowadays, people really need ALD because of the dimensions. And a couple of years ago, what I mentioned was a lot of interest in this material, high quality, low wet etch rate, very conformal, pitch independent, and preferably also a chlorine-free process and low temperature. In the slides and handouts, there are a few more slides a little bit later. I don't think I will be able to cover them today, but you can look up the papers to learn a little bit more about the studies and the things that we learned from the plasma-assisted ALD of silicon nitride studies. But yeah, I cannot cover everything today. And memory devices, of course, there's also ALD is used a lot. DRAM and 3D NAND are in high volume manufacturing. MRAM and PCRAM, of course, they are emerging, I would say. Also here, you have several applications where you use plasma assisted ALD. I show, for example, the 3D NAND. I think you're mostly aware of this. This is memory cells that are stacked. So not only you don't only have them on the surface, but you also have them in the vertical direction. And then you need to etch all these deep holes and slits, and you have to fill up these holes, and you have to replace some of the materials to make a NAND structure. ALD is a critical technology for this application. Without ALD, this would not be possible. And also here, plasma-enhanced ALD is used. I have some information on some applications, but there might be more. One thing where plasma-enhanced ALD is used is to deposit liners in the slits to protect the sidewalls of these structures. Then silicon oxide, as I said, can be very conformal. So that is possible in these deep trenches. Another application, which is kind of special, is that they have these staircase etch, and then they apply some additional silicon nitride to raise the contact landing pad. That's basically for reliability issues, but and actually to avoid etch through. When they etch the hole for the contact, and then they apply some silicon nitride on this structure, but they only apply it at the horizontal part, and that is what we call a topographically selective deposition, where I think plasma-assisted ALD also has a lot of applications in the future. There are some slides about that later, but I don't think I will be able to cover them. But I have at least said this. I also would like to say a few words about encapsulation, because I do know there is a commercial application nowadays. And this is, for example, in OLED displays. People have been talking about OLED displays already for a long time, and also the use of ALD for encapsulation. But apparently, since a few years, there is a commercial product for this. So if you're driving this big car, you have a curved display, and that's an OLED display. And to really make this, to protect that against moisture permeation, people use an encapsulation stack. So in the older days, people were using a combination of PECVD and printed organics, a stack of that. And then I think 3 years ago, right now almost, LG was announcing that they were using also plasma-enhanced ALD to add an additional layer to the stack to improve the properties even more. And that was a plasma ALD plasma-assisted ALD silicon oxide film. And LG was reporting about this, so that is in production. If you look at the internet, you also find companies selling systems. I think often upgraded PECVD systems. They sell that also for plasma-enhanced ALD. Of course, the systems are very similar. And then here you see these big tools, generation 8 tools for PCVD and PALD on these websites. So I think that's showing that there is commercial interest and that they're probably selling these systems for this application. Let me skip this. It's just another example. Okay, let me look at the time. Yeah, let me just talk a little bit about this. I mentioned earlier, often we do regular ALD, AB, AB, AB. You can also do advanced ALD cycles, ABC, 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 for example, or you can do super cycles, where you combine M cycles of one process with N cycles of another process, and you do that in super cycles. That has many applications. I just would like to point out, and I think a very interesting ABC process, maybe not, well, I'm not aware of direct applications. There might be, we just don't know. But this is a low temperature ALD process of metals that we developed. And this is platinum. Platinum you can deposit at high temperatures by oxygen gas and this precursor. But if you want to do that at low temperatures, it doesn't work. We thought, okay, if we now combine this precursor with an oxygen plasma, we can do it also at low temperatures. And yes, we could deposit a film, but at low temperatures, we would get platinum oxide and not platinum metal. And then we thought, okay, maybe we can use now a reduction step, a C step, by a hydrogen gas or hydrogen plasma, and we can reduce the platinum oxide every cycle to platinum. And this is how we were able to make high quality, high purity platinum with a low resistivity and with very nice process conditions at room temperature. So this is what we call an ABC process. There was a question earlier about initial growth. This is a slide where we can explain that. So once you do ALD and you are in steady state conditions, yeah, then we understand the process. But when you start growing, in this case, platinum on aluminum oxide, yeah, then you can wonder what happens in the first cycles. And here we see an effect that we call nucleation delay, because the platinum doesn't really like to grow on the aluminum oxide. And what happens is that you grow particles. This is thermal ALD, by the way. You grow particles initially, and these particles, they will get a critical size, and then they will coalesce, and then you start growing the full film. So initially you have this nucleation delay. Now, if you have a plasma, this nucleation delay can be reduced. You often are more reactive. You can activate the surface a little bit easier. So that's a thing that was also asked earlier. Another thing is that you can use this to make nanoparticles on as support. And this is another ABC process that we developed. This is of palladium nanoparticles. So now the palladium also deposits nanoparticles because of the nucleation delay. And these nanoparticles, they grow as a function of cycles. Now, a very nice thing is here that these particles are about all the same size. They're monodisperse, and the size will now increase with the number of cycles. I saw that there was a question about that. So this is a very nice example, I think. The platinum usually gives a variety of sizes, but this is very monodisperse. The other thing is that we found that if we use this chemistry, palladium with hydrogen plasma, the material is not very pure. There was quite some carbon in the film. And we were able to get that carbon out when doing an ABC process, palladium, HVAC, hydrogen plasma, oxygen plasma. This will not lead to palladium oxide. It will lead to palladium. But now the film will be much purer and have a lower resistivity. So that actually demonstrates that aspect. Another interesting example is cobalt. Cobalt has applications in the back end of line. You can also make cobalt with ALD. Typically, we would use this precursor, cobaltocene, and ammonia. But you can also use a hydrogen-nitrogen mixture. Or you can do nitrogen plasma and then hydrogen plasma sequentially. So these are all plasmas, but here the plasmas are split into sections. And what we found, so these are the 3 different cases. We found that these 2 cases lead to very similar material properties, if you look at this table. But this case, where we split the nitrogen plasma and hydrogen plasma, we have lower film quality, poor film properties. And that was kind of surprising. Well, we say, okay, here we have hydrogen species, nitrogen species. Shouldn't matter, whether they're combined or whether they separate. But apparently it matters. And what we found out is that this plasma also creates a lot of ammonia. And you can make that in a hydrogen-nitrogen plasma. You can create ammonia, and you basically have the same kind of plasma here. Well, if you do the separation, you will not create ammonia. And that is actually, the ammonia is apparently important for the material quality. The fact that we produce ammonia, we were able to determine with mass spectrometry. And we were seeing that if we use hydrogen fraction in nitrogen, we vary the hydrogen fraction from 0 to 100%, we see that we have an optimum of ammonia generation. And apparently this ammonia is very important for this growth process and also for the material quality. So this shows again how important the surface reactions are, because this ammonia is produced at the surface, most likely. So that is another indication of that plasma wall interaction is important. Okay, I will skip the slides on the silicon nitride. Let me see where I continue. Yeah, just maybe a little bit about ion bombardment again, just to keep that repeating. So plasma-assisted ALD, and we have in the plasma we have ions. And this gives me the opportunity to show a nice animation, I think. Let me do this. This summarizes a little bit what I've said before. So this animation is new. It actually demonstrates how a plasma ALD cycle looks like. And now you can use different plasma scenarios. You can have radicals, virtually no ions. So then you will have very soft conditions, sometimes maybe very important. You can have a little bit of ion energy, for example, by using a grounded substrate, but still have ions available. So then you can have enhanced surface reactions. We saw that for silicon oxide, for example, and titania. You can also apply RF biasing. So then you increase the ion energy and you can increase the material quality, maybe have material modification. But of course, you can also overdo it, and then you have too much ion bombardment, and then you have plasma damage. So depending on the application, depending on the material, you have to optimize this. I showed earlier the results for biasing, how we can control this ion energy. And I showed these results, that the tinitride and hafnium nitride improved when we would have some ion bombardment. And here you also see that you should not overdo it, because then the resistivity goes up again. So here we have actually a pretty interesting result that I would like to share. This is actually with tinitride, that if you bias, go from 0 volts to minus 130, you see that some material properties change. So here you see also the stoichiometry. There was a question about that too. But here you see that the oxygen level in the material drops a lot. Here you go a little bit too high, because now the carbon concentration goes up. And we could relate this improvement with biasing, at least at moderate energies, whereby a drop in oxygen content, mostly. Maybe a little bit of stoichiometry, but mostly the oxygen content. And we have some evidence for this too in this plot. This is now hafnium nitride. We saw the same effect. And here we did an experiment where we would apply biasing and then switch off the bias. So the first few cycles we would, well, a couple of cycles we would have biasing, not just a few, but quite a few cycles. And then we would have no biasing. And as a matter of fact, this was the failed experiment because the bias, for some one reason, it switched off. And we thought, okay, we have messed up. But in the end, this was a very, very helpful experiment that went wrong. Because if you look now at the oxygen concentration in the film, so this is where we had bias. This is where we don't have bias. And the nitrogen is the other way around. This is where we have bias. This is where we don't have bias. So you see that the oxygen is really reduced due to the ion bombardment. And even at the sidewall, where you would not expect too much ions, you still have the same effect. So that also shows that ions are also hitting the surface under a small angle. And that's something that we can see, come back to what I showed earlier. Certainly, if you work a little bit higher pressures, you have collisional sheets, and then you might have some ion energy also being provided at the sidewall. Okay. Just to sum up the ion energy, the subset biasing effects. I think this is a slide where we really show what you can do with ion bombardment. And you know, ion bombardment is unique for plasma cases, so that's why I'm highlighting it. Where we can change the material quality. Also the stress we can control. The data is in the paper, where we really can control the stress from tensile to compressive stress by ion bombardment. And we could even actually go to almost zero stress conditions if we would play around with the ion bombardment. There is some additional information on your slides. I will not be able to cover that. I would like to come now to the conclusion of this part. Takeaway messages here. Plasma-assisted ALD has many applications in the semiconductor industry. Also for sacrificial layers, especially patterning is a big application. I once heard that about 1/3 or maybe even over 1/3 of all tools in semiconductor industry are plasma-assisted ALD tools. And I think that fraction is growing. So that shows that plasma-assisted ALD is important. Of course, there are many applications in other fields too. ALD in general, but certainly also plasma ALD allows for many creative approaches to provide the solutions for all kinds of in-film applications. I think that's clear from this story. And I think the plasma-assisted ALD is a valuable extension of the processing toolbox. Again, you only use the plasma when it's really important, but I think there are many cases where that is the case. I will skip this. This is basically just to point out that you need many, that there is a request now for many selective deposition, and I think that can be done by thermal and by plasma-assisted ALD, and certainly also by plasma-assisted ALD, we can have this topographically selective deposition, which is already used in 3D NAND. Okay. Well, that comes to the end. So this is was the outline. So I have covered 4 topics. Hopefully you have learned a lot, and I very much hope that that I have reached the objectives. Of course, there was a lot of information that I had, and there was a lot of things to know, but hopefully it worked out to sufficient extent. I also would like to thank you very much for attending already. And we will have some more questions in a minute, but if there's anything left or there is something that you want to talk about a little bit more, then you please don't hesitate to reach out to me. You have my contact details. You can add me on LinkedIn and reach out to me. I also have here some valuable resources on our blog, but also some other resources that I think are very helpful. So you can have a look at this. There's also some information about process development, for example, image base for high resolution images about ALD. Well, have a look at this. I also would like to acknowledge all the people that have contributed. This is the current group, but also in the past we had many members contributing to the results, and also many of my colleagues in the world have been contributing to the results that I have presented. And then there was some time for questions, I think. These were the submitted questions that were submitted already during registration. I think, and I hope that I have touched upon most of them, but I will we'll look at the questions that you have just submitted and then see what I can answer in the remaining time.
All right, I'll give you a chance to look at those. And thank everyone for attending. We'll take a few minutes for questions. I'll do some closing slides. And again, if you would like to reach out to Erwin, you have his contact information and ways to reach out. He'll also be at ALD, ALE coming up this summer. So,
okay, there were some questions about why plasma increases the growth rate. It doesn't. Well, if you talk about growth rate in terms of nanometer per minute, then so that would be a real growth rate. That is not always the case, but in many cases the case, because you can have shorter cycle times, and the shorter cycle times are, for example, related to the fact that you don't need so long purge times. For example, and this is just an example, if you use water is pretty sticky, so it takes a lot of time to purge it out of the reactor, certainly when you work at lower temperatures. But with an oxygen plasma, if you look at the data that I showed before, you don't need almost any purge time after the oxygen plasma. So that will just some time that you will save, and that's why the growth rate will be higher. The GPC, the growth per cycle, is in some cases higher, but not always. So I'm sure, maybe this was not the question, but the GPC very much depends on the case, and then it very much depends on the chemistry. Okay. Then there was this coming a question back on the dangling bonds. The question is, can you explain why ion energy is positively associated with film quality, but ion energy is associated with dangling bond creation? Well, the influence of the ions can be positive or negative, so it depends on the application. So if you want to have a denser film, then ion energy can be good, or you have maybe a more crystalline film, then ion energy can be good. But there is also a risk that you make some defects, of course, by the ions. So it is an optimization, and it really depends on the application, on the device, and on the material that you're depositing. So there is not a direct general answer to this. Ions and plasma enhanced ALD can have a positive influence, but you have to be sure that that was not a negative influence, and you have to find that out. I think with the knowledge I provided today, and with the references, etc., I think it will be easier for you to find out what's going on, because then you are aware of these two things. But then it really depends on the application, what's good for you and whatnot. What plasma-related problems one could have by using photoresist? Oh, yeah. Yeah, I think well, I'm sure there can be many problems, and people working on patterning, I think they have a lot of issues they have to solve, but I don't see a very obvious problem when you, if you use a photoresist and a plasma. Of course, in plasma etching, you also use the photoresist often, so you can deal with that. So I don't think there is like an obvious problem. But on the other hand, I think there are many things that can go wrong, but it's not something that is directly related with the plasma, I would say. Of course, with a plasma can etch the photoresist. That's also what the issue in etching, of course, where you have photoresist erosion or something like that. But yeah, I don't see a very obvious thing that I could identify here. Yeah, maybe these questions, these answers are not always satisfying, but yeah, it's not so easy to answer them in a short time. Are there any in situ techniques available to determine self-limiting conditions? Yes, ellipsometry, quartz crystal microbalance. So what you basically do is monitor the film growth as a function of the dosing times. And if you look up this paper if you look up the Atomic Limits website, you see 10 steps to define an ALD process, and that will give you the answers how to do it. So there is a very simple document that can be very helpful to design an ALD process and to find out whether it's self-limiting. How do you manage your ALD system to prevent cross-contamination between samples and processes? Well, often people like separate materials. So have a chamber for oxides and having a chamber for nitrides, for example, if you can allow for that. Of course, in production, the tools are only used for one type of material typically. So then you have even multiple tools and you use them only for one material. In more R&D environments, sometimes people separate processes for materials and have several systems. On the other hand, we often use several processes and materials in the same reactor successfully. So depositing a nitride and an oxide in the same system is not necessarily a problem. You might have to run cleans once in a while. We often do this plasma cleaning. The other thing that we often do is condition a reactor wall. And we often do this by running an ALD process of aluminum oxide. Aluminum oxide is very nice to deposit on everything. And then you basically encapsulate the material at the reactor wall and you make them aluminum oxide type. And then it works very well. So, of course, once in a while, we clean the system very thoroughly. We take out the liners and we clean them even manually. But in between, switching from one process to another process, we usually do some aluminum oxide deposition. And the aluminum oxide is also very conformal. And I think that works very well. It might not work in all cases, depending on what you're doing, but we have never really big problems with it. And we do all kinds of things in our reactor, I can tell you.
All right, let's take one final question, Erwin.
Yeah, let's see. There was quite a few more. Yeah, let me just that this is, I think, a nice question to enter. So there was a lot of interest in 2D materials, and the question is, have we looked into this? Yes, I was not able to cover it in this presentation, but there was quite some work on ALD and especially plasma-assisted ALD on 2D of 2D materials, and even on 2D materials. So you will find some literature. But that's certainly something I would like to talk more about in the next time, but I had already too much for this presentation. So I'm sorry about that, but I'm happy to talk more about it directly. Okay, well, there are some more questions left. I will probably will come back to them, or if I can, maybe even write maybe a little blog about this. Some of the questions I think are very interesting for a larger audience, so I might come back to these. And if your question was not answered, feel free to reach out to me. I will do my best.
All right, thank you very much, Erwin. I'm going to go ahead and take the screen and I will share some closing slides with everybody before you head off. And just a reminder to do that evaluation. I shared the link in the chat and I'll also send it via email. Erwin, thank you very much for presenting today's webinar on plasma-assisted atomic layer deposition. I'm sure everybody found some value in this going forward with their phases in work, and want to remind everybody to complete that online evaluation form. Also that we have some online and in-person short courses. Our AVS national short course schedule is a virtual one coming up in March. We have about 8 courses here on various topics, including one on atomic layer etching. So check it out if you're interested. Registration's open. We have our ICM CTF 2023 short course program. These are in-person courses and half days. They're taking place in San Diego during this particular conference. And we have an e-talk coming up on surface microscopy and microanalysis in an industrial research laboratory in April. We'll have registration coming soon for that. As mentioned before, Erwin has worked very hard with ALD, ALE 2023, and over the past several, I think since the inception of this conference, if I'm not mistaken, So please check that meeting out. You can find information on the website, including topics. I believe even 2D is on there. So hopefully there's some abstracts coming for that. We have several other conferences: ICMCTF, MIOMD, gallium oxide, molecular beam epitaxy, and our AVS 69th International Symposium, which abstracts submission has opened up as of today. So check all those out. They can be found on the AVS events calendar. If you're not a current member, we encourage AVS membership. You can find out more about this on the website. It gives you discounts to various events and gives you access to the technical library, where you can find some of our journal topics, including some on ALD and ALE. So check it out. And thank you again. And we appreciate everybody's time. Erwin, thank you again for your presentation. There's a lot of questions out there, so please reach out to Erwin. Check out the ALD, ALE conference. Many ways to reach out to him. So thank you, everyone. And we hope you enjoyed the webinar today. Thank you.
Okay, bye-bye.